Hello there, and welcome to Science for Sleep, where curiosity settles beside you like a familiar companion, and the mysteries of the universe slow themselves down enough for your mind to ease into them without effort. Tonight, we're wandering into something enormous, something so unimaginably large that even seasoned astronomers had to pause when they first realized what they were looking at. It's called El Gordo, a galaxy cluster so massive and so distant that by the time its light reaches us, entire civilizations could have risen and faded, entire forests could have grown and fallen, and countless people could have lived full lives without ever knowing that a titan of the cosmos was shining quietly above them. But that's the way of the universe. It keeps passing on ancient messages whether or not we notice. And sometimes all we need is a gentle invitation to listen. Before we begin unfolding the story of this extraordinary cluster, I'd love to know where you're watching from tonight. What part of the world are you resting in, and what time is it for you right now as you settle in with this quiet exploration? It's always fascinating to imagine listeners scattered across different hours of the evening or early morning, each of us looking up at the same universe yet experiencing it from our own little corners on Earth. Some may be drifting towards sleep, others might be unwinding after a long day, and a few could be watching from the middle of the night when everything feels a little softer, a little slower, and a little easier to take in. If you're finding this relaxing or even just pleasantly distracting, it would mean a great deal if you gave the video a like or subscribed. It helps this cozy space reach others who could use a calm moment, especially when the world feels a bit too full. Now, since you're here, let's ease into the heart of tonight's topic without rushing anything. Take a moment to get comfortable, adjust your blankets or pillows, or simply settle your breathing into a pace that feels natural. Because what we're about to explore isn't just large. It's one of the most enormous structures humans have ever discovered in the entire observable universe. El Gordo isn't just a galaxy cluster. It's a cosmic heavyweight, a true giant assembled from hundreds of galaxies, dark matter, scorching hot gas, and the combined mass of quadrillions of suns. The kind of structure that raises eyebrows in research papers and prompts astronomers to double-check their instruments just to make sure they're not misreading the data. And yet, even with all its size and energy, it has been drifting through space for billions of years, completely silent, long before Earth existed, and long before the idea of humans observing distant worlds had any meaning at all. When people hear galaxy cluster, it's easy to picture something tidy or compact, maybe a group of stars or a few swirls of glowing light gathering closely together. But what we're talking about is something so vast that you could line up millions of entire galaxies between its outer edges and still have room to spare. And El Gordo is on the extreme end of that already extreme category. Its nickname, which means the fat one in Spanish, wasn't chosen in jest. Astronomers were genuinely astonished at its mass. They'd seen galaxy clusters before, they had studied the structure of the universe for decades, and they had built countless simulations trying to predict how these massive systems should evolve. But El Gordo had the audacity to show up far bigger and far earlier than anyone expected, almost like the universe had been holding on to a surprising story, waiting patiently for someone to notice. As we move into its details, there's no need to hurry. Let each idea unfold at its own pace, the way the universe took its time forming El Gordo in the first place. This cluster sits more than 7 billion light-years away from us, meaning we observe it as it looked, when the universe was only about half its current age. Imagine that. Half the stars we see today hadn't yet formed, the Milky Way was still developing its spiral arms, and Earth was nowhere near becoming the blue and green home we know. Yet there El Gordo was, a massive accumulation of galaxies already well underway. It forces us to ask how something so enormous could have assembled at such an early stage in cosmic history. Typically, structures of its scale take an incredibly long time to form, but there it was, defying expectations, quietly broadcasting its immense presence across billions of light-years of space. When astronomers first encountered it, they didn't set out looking for anything unusual. That's often how discoveries unfold. Scientists peer into the sky with a plan to study something predictable, and then a signal appears that doesn't fit neatly with any expectation. El Gordo was noticed because something about the light passing through its region didn't behave the way ordinary cosmic structures behave. Observations showed distortions and temperature signatures that were far too intense for a typical cluster. The cosmic microwave background, a faint afterglow left over from the early universe, was being shifted in a way that revealed an immense concentration of mass. These distortions weren't subtle. They were dramatic enough that the team studying them had to consider the possibility that they were observing something far larger than anything previously catalogued at that distance. It's always interesting to think about how long it takes for the scientific community to accept discoveries like this. Observing a cluster is one thing. Proving that it is indeed as massive as it appears, especially when it challenges existing models, takes careful verification. Scientists cross-check gravitational lensing, X-ray emissions, optical data, and subtle temperature shifts in the background radiation. Each line of evidence tells a slightly different part of the story, and together they paint a picture that becomes difficult to deny. With El Gordo, these lines of evidence didn't simply confirm its mass, they confirmed that this cluster was a cosmic outlier, something that shouldn't have been possible according to earlier predictions about how quickly matter could gather in the young universe. As we drift through the details, try to imagine the scale without straining yourself. You don't need to hold exact distances or masses in your mind. You might simply picture a collection of galaxies stretching across an expanse so wide that it would take light millions of years to cross it. You could imagine hundreds of billions of stars in each of those galaxies, each star with planets circling it, each planet with its own quiet history, and all of that packed inside a single cluster that formed when the universe was still figuring out its long-term structure. It's not important to picture it accurately. What matters is letting your mind gently grasp just how much mass and motion must be involved for a system this size to exist. One of the most intriguing aspects of El Gordo is that it appears to be the result of a massive cosmic collision. Two galaxy clusters, each already enormous, seem to have slammed into each other in a kind of slow-motion crash that unfolded over hundreds of millions of years. When clusters collide, the galaxies within them mostly pass by each other, because the space between stars is immense. But the hot gas that fills the clusters doesn't pass quietly. It slams together, heats up, and leaves behind a turbulent trail that astronomers can detect from extraordinary distances. Dark matter, the invisible mass that shapes galaxy clusters, also plays a central role, revealing itself through gravitational lensing as it subtly warps the paths of light moving through the region. There's something unexpectedly calming about considering these enormous collisions. Not because they're gentle, but because they unfold on timescales so slow that even calling them collisions feels almost too dramatic. They're more like long, drawn-out interactions where gravity gradually pulls two systems together until their outer regions begin to merge. Over time, the galaxies inside adjust to new orbits, new gravitational centers, and new patterns of interaction. When astronomers look at El Gordo, they see evidence of this grand merging, a snapshot frozen in time from billions of years ago, preserved for us to study long after the collision finished playing out. Even though these interactions are incredibly energetic, there's no sound in space, no shock wave you would hear if you were floating nearby, just motion, heat and gravity working quietly over vast distances. That's one of the striking things about the universe. Even its most violent events are silent. They're enormous and powerful, yet lack the explosive noise we instinctively associate with chaos. Instead, everything moves through the vacuum without a single echo, leaving behind shapes and structures that we can only observe through the faint light that eventually reaches us. As we continue, it's helpful to remember that El Gordo isn't just an impressive statistic. It's part of the larger story of how the universe builds structure over time. Galaxy clusters are some of the largest bound objects in existence. They form slowly as gravity draws galaxies into common regions, allowing them to orbit and interact. but El Gordo's presence at such an early cosmic epoch forces researchers to reconsider their timelines. If something this massive was already formed 7 billion years ago, perhaps the universe is more efficient at building clusters than previously assumed. This opens up questions about dark matter, the role of cosmic expansion, and the speed at which early structures came together. The light from El Gordo also carries with it a kind of time capsule quality. Because it took billions of years to arrive, observing this cluster allows scientists to infer what conditions were like long before Earth existed. Looking into the deep universe isn't like looking at something far away in everyday experience. It's more like looking into the past itself. What we see from El Gordo is a snapshot from a younger universe, a picture taken long before humanity existed to give it a name. By studying it carefully, astronomers can understand the interplay between dark matter, gas, and galaxies in a time when the universe was much denser and more active. The nickname El Gordo might sound playful, but the scientific implications behind it are anything but casual. It hints at an object so massive that its very existence stretches the boundaries of our current models. If the early universe was able to form something this large, it forces us to re-evaluate assumptions about cosmic growth, dark matter behavior, and the distribution of mass shortly after the Big Bang. As we explore deeper into these concepts in the next parts of our journey, the goal won't be to overwhelm you with numbers or equations. Instead, we'll continue unfolding the ideas at a pace that lets your thoughts settle comfortably, letting the concepts drift in without pressure or urgency. You might even find that as the narrative moves forward, the details blend into something pleasantly steady, the kind of information rhythm that helps quiet the noise of the day. That's often the unexpected benefit of learning about the universe in slow, gentle steps. The mind becomes occupied just enough to ease into rest, yet not so engaged that it becomes tense or alert. And as El Gordo continues to reveal itself, there's more than enough intrigue in its history, structure, and scale to keep the story moving without haste. When people hear that the universe is full of enormous structures, it's easy to imagine that the sky is mostly empty with only a sprinkling of stars and a few scattered galaxies. But the truth is that the cosmos has always been building things on scales that are almost impossible to picture in any meaningful way. From expansive filaments to long stretches of dark matter and the clusters that form where these strands intersect, the universe has spent billions of years collecting its material into shapes that would put anything we're familiar with into a distant category of smallness. And among these quiet giants, there are some that become so large, so unexpectedly heavy, that even seasoned astronomers feel a familiar sense of disbelief when they first encounter them. El Gordo belongs to that rare group, not just large, but something that clearly outpaced everything around it. Before diving into its uniqueness, it helps to have a sense of what it means for anything in the universe to grow this big without anyone urging it along. Galaxy clusters form over long periods, shaped by the steady tug of gravity bringing smaller groups of galaxies together, merging them into larger systems until the end result becomes a cluster. This process is slow and generally predictable. Most of the clusters we know fit comfortably within the expectations set by simulations, meaning their size and mass are simply reflections of the time they have had to form and the amount of matter available to pull in. But when a cluster appears that is far too massive for the time period it exists in, the scientific community takes notice. It tells us something unexpected happened, something faster or more efficient than the usual pattern. To appreciate El Gordo's unusual growth, it's helpful to look at the landscape of cluster formation. In the early universe, matter was still settling into larger shapes. Stars were forming inside galaxies. Galaxies were joining into small groups, and those groups eventually became the seeds of clusters. But this growth is usually slow because space is extraordinarily wide. Distances between galaxies can be so immense that it takes billions of years for gravity to pull them together, and even when they start drifting toward one another, The merging process is more like a long, drawn-out approach than a sudden crash. Cluster formation is a gradual tightening of orbits and slow mixing of structures, which means that very massive clusters early in cosmic history aren't expected to be common. Most clusters at the same age as El Gordo were smaller, less developed, and still in the middle of their assembly phase. They were collecting material, but they hadn't yet reached their full size. El Gordo, on the other hand, seemed to have skipped several steps, almost as if it had found a shortcut to becoming one of the heaviest clusters known. Its mass was so significant compared to others of its age that astronomers questioned whether the early universe might have been more efficient at forming clusters than their models predicted. If something this massive existed at that time, what else could be out there that hasn't been found yet? That quiet uncertainty brought new curiosity into the study of early cosmic structure. The strange thing about clusters is that even though they are enormous, they rarely look chaotic. Their vastness gives them a calm appearance, especially in images where they appear as gentle clouds of galaxies slowly drifting around a central region. It's easy to forget that each of those galaxies holds billions of stars. From a distance, clusters seem serene. Nothing looks rushed. Galaxies orbit one another without sudden motion. Even a collision between clusters, the kind that may have produced El Gordo, unfolds so slowly that calling it a collision almost seems misleading. It's more like a long interaction that eventually produces a new, larger structure. Still, among these quiet giants, some stand out for the simple reason that they gathered more mass than their neighbours. Many clusters grow steadily, a few grow dramatically. And then, once in a long while, there is one that outpaces everything around it. El Gordo became one of those. Its mass alone set it apart. But what really caught everyone's attention was the point in time at which it already existed. It wasn't supposed to be there yet, or at least not in the form it had taken. The early universe didn't offer much time to assemble such a heavy cluster, so its presence raised a long list of questions that researchers were eager to explore. When studies first began, astronomers expected to categorize El Gordo as a cluster with unusual extra gas, or perhaps an exaggerated temperature measurement. Although surprising observations happen, they often have simpler explanations. But as data accumulated, every line of evidence pointed towards something massive. X-ray observations revealed extremely hot gas. Gravitational lensing showed strong warping of background light. Temperature shifts in the cosmic microwave background demonstrated that this cluster was pushing on surrounding radiation in a way only very massive systems can. Each form of measurement acted like a different vantage point, and all of them agreed on one thing. The structure was heavy, far heavier than anyone had predicted for that era of the universe. Other clusters in the same distance range didn't come close. They were large, certainly, but they fell within the typical mass range expected for their age. El Gordo did not. It was so massive that even comparisons with clusters much closer to Earth, which had twice as much time to grow, made astronomers pause. There weren't many local clusters that outmatched it. And when something is that rare, scientists naturally begin asking more questions about how it formed, how early its growth started, and what the surrounding environment must have been like to make such rapid accumulation of matter possible. In the search for understanding, researchers often turn to computer simulations. These models attempt to recreate the behaviour of the universe from its earliest moments, following how matter clumps together into larger structures over time. These simulations are powerful tools, but even they struggle to produce a system like El Gordo at its observed age. When a cluster becomes so extreme that it sits at the far edge of what simulations permit, it makes researchers wonder whether the assumptions in their models need adjusting. Maybe the early universe had conditions that favoured faster cluster formation. Maybe dark matter behaved slightly differently than expected. Or maybe El Gordo is simply an outlier that challenges existing theories without contradicting them. It's tempting to imagine El Gordo pushing its way ahead of other forming clusters, as if there was some kind of race involved. But of course, there's no competition in cosmic evolution. no sense of urgency, no awareness among galaxies or dark matter. The cluster simply accumulated mass efficiently, possibly because the region it formed in had a higher density of matter than other areas. That would have given it more material to pull in. High-density regions in the early universe act as the seeds for large-scale cosmic structures. Some remain modest in size, others grow over billions of years into clusters, and a few, like El Gordo, capitalize on their environment in exceptional ways. The more astronomers studied the cluster, the more they realized that its history likely involved a major merging event. Two large clusters combining into one would lead to a rapid increase in mass, and the resulting structure would show signs of such a collision. Observations revealed exactly that. There were temperature irregularities in the gas, gravitational signatures consistent with dark matter from merging systems, and patterns in galaxy motion that hinted at a dramatic encounter long before the light from that event reached us. Even if the interaction was slow from a human perspective, on cosmic scales, it was significant enough to leave behind long-lasting clues. If you picture two enormous clusters beginning to merge, it becomes easier to understand how something so massive might come together unexpectedly early. The merging would create a spike in mass, pushing the cluster into a category much heavier than usual. And because the collision occurred billions of years ago, the shock waves and heated gas left behind would still appear in observations today. El Gordo's temperature, structure, and movement all support the idea that it didn't grow only through steady accumulation. It grew through a dramatic interplay of two already large clusters. The result was a system that exceeded expectations for that cosmic time period. While that might explain how the structure outgrew everything around it, the details still leave researchers with a sense of curiosity. Colliding clusters are not rare on cosmic scales, but the speed and energy implied by El Gordo's formation make it stand out. It's not unusual in a mild sense, the way a slightly larger than average cluster would be. It's unusual in a way that forces astronomers to reconsider how quickly such massive systems can form. The early universe had less time to produce these giants, yet El Gordo formed anyway, large enough that it challenges the upper limits of early cluster formation. In the broader picture of cosmic evolution, El Gordo fits into a long lineage of enormous structures. Across the universe, clusters form at the intersections of filaments, in what's sometimes referred to as the cosmic web. These filaments feed matter slowly into clusters, which then continue growing. But not all clusters grow at the same pace. Some environments are richer in material, some have denser initial conditions that give them an advantage, and some are simply the result of early mergers that quickly push them into higher mass categories. All of these factors play a role in shaping the quiet giants of the cosmos. Still, El Gordo didn't just join that category, it exceeded it. It stands among the heaviest clusters known, and it reached that status while the universe was still young. Other clusters in the distant universe are massive too, but few compare to its scale. And even among those that do, El Gordo continues to hold its position as one of the most extreme examples ever found. Its presence reminds researchers that the universe is not always as predictable as a model might suggest. There are always exceptions, there are always surprises, and sometimes those surprises reveal gaps in our understanding of how matter behaves on the larger scales. Thinking about these enormous structures can feel strange at first, because the numbers involved are beyond anything we encounter in everyday life. But when described slowly, without rushing to the next concept, they become easier to grasp. A cluster is simply a collection of galaxies held together by gravity. A large cluster holds more galaxies. A very large one holds even more. And El Gordo holds so many that the combined mass reaches into the territory of quadrillions of suns. Even if that number doesn't mean much intuitively, what matters is knowing it's a scale well beyond what most clusters manage to achieve. Astronomers never set out expecting to stumble upon something that would end up reshaping conversations about the early universe. Most discoveries begin with routine surveys, ordinary nights of data collection, or long-term projects designed to map large parts of the sky. That's usually how it goes. You gather data, process it, compare it to existing catalogues, and hope that somewhere in those countless measurements something interesting might be waiting. But El Gordo didn't appear through a dramatic moment or a sudden cosmic spectacle. It emerged quietly, through signatures that at first seemed too intense to match ordinary clusters, and through hints that left astronomers wondering if their instruments might be picking up something else entirely. The earlier signs didn't arrive as a clear image of a huge structure, they came as distortions. That's often how astronomers detect massive objects in distant parts of the universe. A galaxy cluster doesn't always stand out in the way a bright star or nebula might. Instead, it influences the light behind it. That subtle bending of background light, caused by gravity, acts like a fingerprint. When the bending is too strong to come from a normal cluster, researchers begin paying closer attention. In El Gordo's case, this bending wasn't subtle. It was stronger than expected, and it showed up in ways that were difficult to dismiss as noise or coincidence. Before identifying the cluster itself, scientists first noticed unusual patterns in the cosmic microwave background. This faint radiation left over from the early universe covers the entire sky like a thin, uniform layer. When a massive cluster sits in front of it, the hot gas within that cluster interacts with the radiation. This interaction, known as the Sunyaev-Zeldovich effect, shifts the temperature of the background slightly. Not dramatically, but enough for sensitive instruments to detect. When teams analysing this effect looked at the region that would later be named El Gordo, they found something striking. The temperature shift was unusually large, far too large. At first, it wasn't clear what was causing it. Background interference or an unrelated source could sometimes create confusing signals. But this shift had the pattern of hot gas from a massive cluster, and the more researchers examined it, the more it looked like the signature of something much heavier than usual. The early data alone wasn't enough to declare anything unusual, but it sparked curiosity, the kind that encourages follow-up observations rather than the kind that can be dismissed. After that, optical surveys began focusing on the area in question. Optical imaging is one of the most straightforward ways to identify galaxy clusters. You look for a concentration of galaxies in a particular region and determine whether they share similar redshifts, meaning they are at the same distance from Earth. When astronomers pointed their instruments at the location flagged by the earlier temperature data, they saw something unexpected. There were galaxies there, many of them, and they seemed to be part of a large cluster. But clusters at that distance were normally smaller or less mature. This one was crowded, a gathering of galaxies so rich that it stood out as soon as the data was processed. Still, richness alone didn't confirm anything unusual. Some clusters simply contain more galaxies than others, depending on their formation history. The real question was mass. A cluster can contain many galaxies without necessarily being extremely heavy. Much of a cluster's mass is not in the galaxies themselves, but in the hot gas and dark matter surrounding and threading through them. So the next step was to examine the hot gas. Scientists turned to X-ray instruments to measure the gas temperature and distribution. Hotter gas suggests deeper gravitational wells, meaning more mass. When the X-ray data arrived, it immediately added weight to the growing suspicion. The gas wasn't moderately hot. It was extremely hot, hotter than typical clusters from the same era. That level of heat could only come from a very deep gravitational well. In other words, a very massive structure. X-ray observations confirmed that the region wasn't simply a bright patch caused by some isolated phenomenon. It was a true cluster and a substantial one. The temperature and spread of the gas suggested a system formed from significant merging activity, the kind of turbulence that leaves behind heated trails detectable even billions of years later. By this point, the team analysing the data began to realise that they had stumbled onto something unusual, not just another entry in a long catalogue of galaxy clusters. But even with optical and X-ray data, mass estimates still require careful checking. To get a more precise sense of the total mass, astronomers turn to gravitational lensing. This method looks at how the cluster distorts the shapes of galaxies behind it. When light passes near a massive object, gravity bends its path, causing the background galaxies to appear stretched or curved. The more mass the cluster has, the more pronounced the effect becomes. In El Gordo's case, the lensing distortions were strong enough to signal that the cluster wasn't simply on the heavy side. It was entering the category of extreme clusters, the kind that researchers rarely encounter at such distances. Combining these different observations takes time because each method highlights a different part of the cluster structure. Optical data shows how many galaxies are present and how they move. X-ray data reveals the temperature and density of the gas. Gravitational lensing exposes how much mass exists in total, including dark matter which is invisible through other means. The Sunyaev-Zeldovich effect adds yet another perspective by showing how the cluster interacts with the cosmic microwave background. When every independent measurement supports the same conclusion, astronomers gain confidence that what they're observing is real, and not a result of faulty data or mistaken assumptions. When researchers looked at the combined datasets for El Gordo, the evidence formed a consistent picture. This wasn't simply a large cluster. It was one of the most massive clusters ever detected at that distance. Not only that, but the data suggested a merger in progress, or one that had occurred relatively recently in cosmic terms. The shock-heated gas and asymmetric distribution of galaxies pointed toward a dynamic history. Two clusters of substantial mass had likely collided, producing the overwhelming structure observed today. At this stage, the scientific community began taking notice. When something challenges expectations about cosmic growth, researchers want to understand what makes it unusual. El Gordo's existence at such a young cosmic age raised important questions about how the early universe behaved. If a cluster this massive had formed so long ago, maybe the common assumptions about how quickly matter can clump together needed refining. Or maybe the region of the universe where El Gordo formed had particularly dense initial conditions, giving it a head start that most clusters didn't have. Follow-up studies using larger telescopes and more sensitive detectors strengthened the findings even further. Optical surveys with deeper imaging showed that many of the galaxies within the cluster were actively forming stars or displaying features typical of merging systems. That was consistent with the idea of two clusters colliding. Higher resolution X-ray imaging revealed shock fronts and temperature gradients that pointed toward large-scale turbulence. Those are the fingerprints of a dramatic merging event, the kind that could rapidly build a massive structure. An improved gravitational lensing map showed significant distortions across wide regions of the cluster, reinforcing the idea that its mass was truly enormous. Every new observation added another layer of detail. None contradicted the earlier measurements. If anything, they confirmed that the initial mass estimates had been correct. El Gordo wasn't just heavy, it was extraordinarily heavy for its age. And that's what makes it stand out. Not all massive clusters pose a challenge to cosmic models. Many heavy clusters exist closer to Earth, where the universe has had more time to assemble them. But El Gordo is seen as it was more than 7 billion years ago, which means it formed much earlier than clusters of similar size. That timing is the key. The earlier in cosmic history a cluster forms, the more difficult it is for it to reach extreme mass. Astronomers began presenting their findings at conferences and publishing their results in journals. The cluster quickly gained attention not just because of its mass, but because of what it implied about the early universe. Researchers started questioning how common such systems might be. If El Gordo existed at that time, were there others of similar size waiting to be discovered? Or was it a rare outlier in a universe that mostly followed predictable patterns? Those questions sparked searches in other deep survey regions, as scientists hoped to discover whether this cluster was unique or part of a larger trend. Although the discovery process involved multiple instruments and methods, the story kept returning to the same realization: a distant signal, a temperature shift, a patch of sky that refused to behave like an ordinary cluster, a system whose mass forced astronomers to consider the possibility that they were looking at something exceptional. And as the evidence built up, hesitation gave way to acceptance. The cluster had revealed itself through quiet signals that only careful observation could detect, and once everything aligned, it became clear that astronomers had found something worth studying in depth. Even now, researchers continue analysing El Gordo to understand what made it grow so rapidly. They look at the galaxies within it, the velocities they travel at, the distribution of dark matter, the temperature of the gas, and the ways in which the cluster interacts with light from behind it. Each observation adds something new, showing how a structure becomes extraordinary not through a single characteristic, but through many factors aligning in an unusual way. When astronomers first noticed the region that would later become known as El Gordo, they weren't searching for something extraordinary. They were looking at faint signals in the background of the universe, the kind of small shifts that normally blend into the larger picture of cosmic structure. But occasionally a signal shows up that refuses to be ignored, the kind that leaves researchers pausing long enough to wonder whether what they're seeing is the start of a much larger story. That is exactly what happened in the earliest observations that hinted at the existence of this enormous cluster. What drew attention wasn't a bright object or a dramatic cosmic event, but a handful of unusual patterns that didn't quite fit the usual signature of distant systems. It started with a temperature shift in the cosmic microwave background. This shift wasn't large by everyday standards, but it was significant enough to stand out against the otherwise even spread of background radiation left from the early universe. The cosmic microwave background is nearly uniform, with only slight variations, so astronomers pay close attention when an area shows a distinctive deviation. In this case, the shift came from photons losing energy as they passed through extremely hot gas. That loss pointed to something massive sitting between Earth and the background glow. Normally the scale of the effect matches clusters that are large but not extraordinary. This signal, however, indicated gas far hotter and denser than expected. The Sunyaev-Zeldovich effect, which causes this temperature shift, is an essential tool in measuring cluster mass, but it doesn't immediately reveal the full structure. It's more like a hint, something that says, "Look here." When astronomers saw this particular signal, they didn't assume anything incredible at first. They simply marked the region as interesting. But the unusual strength of the effect was hard to dismiss. It wasn't subtle. It was bold enough that dismissing it as a statistical fluctuation didn't seem reasonable. So they planned deeper observations. As more teams began examining the same patch of sky, additional signals started to surface. Instead of fading under scrutiny, the area became more compelling. Optical surveys pointed out that the region wasn't empty. There were signs of many galaxies, too many for an ordinary cluster at that distance. The galaxies were dimmer than nearby ones because of the vast distance their light had travelled, yet their distribution suggested that they were part of a coherent system. When researchers compared their redshifts, more evidence emerged. These galaxies weren't randomly aligned. They were travelling through space at similar distances and velocities, indicating they belonged to the same large structure. Those findings alone didn't confirm anything unusual, but they added another piece to the puzzle. A heavy cluster, especially a distant one, affects the motion of its galaxies, so their velocities can offer clues about the mass of the system. Early measurements showed that some galaxies were moving at impressively high speeds relative to one another, suggesting the gravitational pull binding them was extremely strong. That pointed toward a deep gravitational well, and deep wells imply large mass. X-ray observations soon followed, providing yet another angle on the system's hidden nature. X-ray telescopes are particularly sensitive to the hot gas that fills galaxy clusters, and this region emitted X-rays that were noticeably intense. Hot gas in clusters can reach tens of millions of degrees, heated by the combined gravity of thousands of galaxies and the dark matter halos around them. In El Gordo's case, the gas temperature suggested energetic interactions, the kind that often accompany collisions between massive clusters. The X-ray brightness and temperature indicated a massive structure with turbulent activity, something far beyond a typical cluster at that distance. Researchers analysing the X-ray data realised that the distribution of hot gas wasn't smooth. There were asymmetries that didn't match a relaxed, mature cluster. Instead, the gas appeared disturbed, as if two enormous systems had collided and left behind heated trails. These disturbances revealed shock fronts, areas where gas was compressed and heated as two structures passed through each other. When shock fronts are present, the system is usually classified as a merging cluster, and merging clusters often have very high mass. These signs continued collecting until it became clear that something much bigger than expected was shaping the region. But the most decisive evidence came from gravitational lensing. Light from distant galaxies behind the cluster appeared stretched and distorted, bent by the immense gravity of the unseen mass. The distortions were not mild. They reached a level that only very massive systems can produce. When astronomers created lensing maps, the patterns clearly outlined dense concentrations of dark matter. These concentrations matched the idea of two merging clusters, each with its own dark matter distribution, now overlapping in a dramatic interaction. The lensing strength alone was enough to indicate a genuinely enormous system. When researchers combined the lensing data with measurements from the Sunyaev-Zeldovich effect, the X-ray observations and optical galaxy counts, the combined picture became increasingly compelling. Each method pointed to a cluster with a mass far exceeding normal expectations for its age. No single measurement stood out as an error or anomaly. Everything supported the same conclusion across independent methods. As more analysis took place, scientists noticed another pattern. The gas and dark matter didn't perfectly overlap. The galaxies also had their own spatial distribution. In merging clusters, gas and dark matter respond differently during collisions. Gas heats up and slows down because of friction. Dark matter passes through almost unaffected because it interacts very weakly with other matter. This difference creates separations that can be detected through careful observation. El Gordo displayed exactly that behaviour. The gas had shifted in one direction, while the dark matter concentrations indicated by lensing were slightly offset. That separation supported the idea of a recent or ongoing collision. Beyond that, the velocities of galaxies inside the cluster painted an additional picture of just how energetic the system was. The measurements showed that galaxies were moving at tremendous speeds within the cluster's gravitational field, faster than velocities typically seen in younger or smaller clusters. Only very deep gravitational wells can sustain such high-speed motion. The fact that these movements were present at such an early cosmic epoch strengthened the conclusion that this structure was not only massive, but unusually so for its position in time. Every new method used to measure El Gordo added weight to the understanding that this was not a normal cluster. Other massive clusters existed, but most were much closer to Earth and in a more mature universe. The cluster forming such an enormous structure, while the universe was still comparatively young, challenged expectations about how quickly large systems can develop. As astronomers continued analysing the data, they began to realise that the signals indicating extreme mass weren't isolated to one part of the cluster. The entire region supported the same interpretation. The temperature distribution, the Sunyaev-Zeldovich signature, the X-ray emissions, the lensing strengths, the galaxy velocities, and the overall structure aligned into one coherent conclusion. Something truly immense had formed billions of years earlier than expected. More observations followed, not because researchers doubted the cluster's existence, but because they wanted to understand its behaviour in greater detail. Each new instrument brought clarity. Higher resolution images revealed structures that had been blurred in earlier data sets. More precise spectroscopic measurements refined the velocities of galaxies. Additional X-ray data clarified the hot gas patterns. Every update helped solidify the understanding that this cluster was exceptional. The signals that first hinted at something interesting eventually transformed into evidence of a genuine outlier. They showed astronomers that the early universe may have been capable of assembling enormous structures faster than previously thought. Some researchers suggested that the cluster may have formed in a region of unusually high density, giving it access to more matter than average. Others proposed that the merging event accelerated the growth significantly, enabling the system to reach extreme mass quickly. The signals also led scientists to reconsider small details about how dark matter behaves during collisions. El Gordo provided a natural experiment for observing dark matter distributions under extreme conditions. Because dark matter doesn't interact much with normal matter, its distribution after a collision can reveal how it behaves when galaxies and gas pass through one another. El Gordo's structure allowed astronomers to compare where dark matter clustered versus where hot gas collected, offering clues about the invisible components of the cluster. With each signal combined into a single understanding, astronomers recognized that they weren't simply seeing a large cluster. They were seeing evidence of early cosmic assembly on a scale that demanded further study. The signals that first appeared as small hints grew into detailed insight about how clusters merge, how mass accumulates, and how the early universe may have been more complex than earlier models suggested. Even now, the signals continue to attract attention, because researchers know they haven't extracted everything they can from them. As instruments improve and observational techniques become more refined, older data often takes on new meaning. El Gordo remains an active subject of study, not just because of its size, but because those early signals transformed it into one of the most intriguing cosmic structures ever found. Most people hear the word cluster and imagine something small or compact, maybe a tight group of stars gathered in a neat pattern. But a galaxy cluster isn't just a handful of stars or even a handful of galaxies. It's a structure so enormous that it makes individual galaxies look like grains in a landscape far wider than anything our senses are designed to grasp. To understand why El Gordo is able to stand out among these giants, it helps to take a moment and picture what a galaxy cluster actually is. Not in precise diagrams or dramatic illustrations, but in simple terms that allow the mind to settle into the scale without strain. A cluster is the universe's way of gathering matter into its largest gravitationally bound systems. Galaxies don't drift around in complete isolation. They tend to group together because gravity gradually pulls them into collective formations. Over enough time, these groups merge into larger sets, and eventually those become full clusters containing hundreds or even thousands of galaxies. The universe didn't build these structures quickly. It took billions of years for them to form through the slow movement of matter drifting together, combining and recombining as gravity shaped them into the large systems we see today. Each cluster contains different components. The galaxies inside are the most visible part, the ones you might see in optical images. These galaxies can be spiral, elliptical, irregular, or anything in between. They orbit through the cluster in long arcs, influenced by the gravity of everything around them. But the galaxies themselves are only a small fraction of the total mass. A much larger portion is made up of hot gas, millions of degrees hot, filling the space between galaxies. This gas is so energized that it emits X-rays strong enough for telescopes to detect from extraordinary distances, and beyond that, there's the component that remains invisible to regular telescopes, the one that holds everything together more strongly than anything else. Dark matter. Dark matter makes up most of the mass in any galaxy cluster. Without it, the galaxies would drift apart. The gas would not remain bound. The structure itself would fragment. Dark matter forms a kind of unseen scaffolding, a gravitational framework that keeps everything in place. Even though it cannot be observed directly, its presence becomes clear through its gravitational effects, especially through gravitational lensing, where light bends around it as it moves past. When all these components combine, the result is a cluster, one of the universe's most impressive constructions. Most clusters follow general expectations about how they form. They develop slowly. They gain mass through the merging of smaller systems, sometimes experiencing more energetic events such as collisions with other clusters, but overall their growth tends to reflect the passage of cosmic time. Older clusters are usually larger because they've had more time to pull in matter. El Gordo doesn't behave quite like that. It isn't just a heavy cluster. It's a heavy cluster that existed long before it should have reached such a scale. That timing is what makes it notable. It's one thing for a cluster to become massive after billions of years of steady growth. It's another thing entirely for a cluster that we see as it existed over 7 billion years ago to have already gathered so much material that it rivals or surpasses many modern clusters. This is what makes it break the normal rules of cluster formation. To see what breaking the rules means in this context, it's important to understand what normal expectations look like. Most clusters in the early universe were still in their growth phase. They were forming from the material available in their region. This process involved merging, accretion, and the gradual build-up of dark matter halos. These clusters were often smaller than their present-day counterparts, because the universe simply hadn't existed long enough for extremely massive structures to take shape. Large clusters do exist at earlier times, but they tend to be less massive than the giants we find in the nearby universe. El Gordo stands out because it bypassed that slow-scale progression. At an age when the universe was only about half of what it is now, it had already reached a mass that would typically require far more time to assemble. The cluster wasn't just massive on a relative scale, meaning massive compared to others at its distance. It was massive on an absolute scale. The total mass estimates place it among the top tier of clusters ever seen in any era, which is why astronomers had so many questions about how it grew so quickly. To understand why this is surprising, imagine the timeline of matter assembly in the universe. After the Big Bang, matter wasn't distributed evenly. There were slight variations in density, tiny irregularities that would slowly grow under gravity. The denser regions attracted more matter, becoming the seeds of future galaxies and clusters. That growth, however, was limited by time. Forming a massive cluster takes billions upon billions of years of gradual gathering. It doesn't happen overnight. If you look at clusters closer to Earth, which we see in the universe as it exists today, many of them are extremely massive because they have had nearly the entire age of the universe to build up their mass. El Gordo didn't have that luxury. The light we observe from it comes from a time when the universe was still young, yet the cluster had already achieved a mass that rivals some of the heaviest modern clusters. That alone strains expectations, but El Gordo goes further by also displaying signs of a major collision event. This merging activity hints at two already large clusters coming together, an event that would dramatically boost its mass in a short period. For such an event to occur so early means the two smaller clusters that combined to form El Gordo were themselves unusually massive. The situation becomes a chain of unlikely developments that all had to line up for this cluster to exist in the form we observe it. The fact that El Gordo is a merging cluster adds more complexity to the idea of it breaking the rules. Merging clusters offer some of the most energetic events in the universe, outside of things like black hole collisions. When two clusters combine, the galaxies within them don't crash into each other directly because they are spaced too far apart. But the hot gas between the clusters collides, generating shock waves that heat the material to high temperatures. Dark matter passes through relatively unaffected, but the gas slows down and compresses, creating a temporary separation of the cluster's components. This separation was clearly visible in El Gordo, a sign that the collision took place not long before the light we observe left the cluster. What this means for rule breaking is that El Gordo not only grew large in an unusually short time, but did so through a dramatic event that requires both progenitor clusters to already be substantial. That combination makes astronomers rethink how dense regions of the universe could have been early on. If early matter distribution allowed for such growth, perhaps clusters like El Gordo were forming in pockets of higher density than models currently assume, or perhaps the collision itself was so energetic that it produced mass concentrations faster than expected. Understanding the structure of a cluster also helps explain what makes El Gordo stand out. A typical cluster has a fairly symmetric shape if it's been stable for a long period. Galaxies orbit smoothly within the gravitational potential well. The hot gas forms a relatively smooth halo around the centre. Dark matter distributes itself in a shape that aligns with the cluster's gravitational pattern. But El Gordo isn't symmetric. It doesn't have the relaxed shape of an old settled cluster. The distribution of galaxies suggests directional movement. The hot gas has regions of high temperature that mark shock fronts. The dark matter maps reveal offsets between different parts of the system. All these observations show that El Gordo was not sitting idle when we observe it. It was in the middle of complex internal dynamics, and that level of activity points toward a merging event powerful enough to rapidly accumulate mass. This is important because a merging event of that scale is statistically unlikely in the early universe. It requires both participating clusters to be unusually massive, and it requires the timing of their collision to align perfectly with the snapshot of cosmic history we observe. Another layer worth understanding is the composition of clusters in general. The galaxies within them are usually classified by type. In many mature clusters, elliptical galaxies dominate because mergers over time disrupt the formation of new stars. Spirals become less common. But in younger clusters, there's often a mix. Early clusters may still have galaxies forming stars at high rates. El Gordo shows a significant number of galaxies that appear to be active, meaning star formation was still underway at the time. This combination of active galaxies, hot gas, and dark matter offers clues about how far along the cluster was in its development. The star-forming galaxies show that the system hadn't settled into a quiet, mature state, reinforcing the idea that it was a young but extremely massive cluster. The presence of active galaxies alone doesn't break rules, but combined with the cluster's total mass and merger evidence, they help reveal how unusual the system truly is. Gas temperature is another important clue. Clusters with high mass tend to have extremely hot gas because the gravitational energy of the cluster compresses and heats the material as it falls inward. El Gordo's gas was hotter than many clusters of similar age. That heat came partly from the merging event, but also from the immense gravitational potential of the cluster itself. The hot gas increases the strength of the Sunyaev-Zeldovich effect, making the cluster more detectable in microwave surveys. This strong signal was one of the first hints that something unusually large was present. What's striking is that El Gordo checks every box that indicates extreme mass: high galaxy velocity dispersions, strong gravitational lensing, intense X-ray emissions, powerful Sunyaev-Zeldovich signature, asymmetric gas distribution, and active merger evidence. Most clusters might show a few of these features, but rarely all at once, especially in the early universe. When a cluster displays so many indicators simultaneously, it raises questions about how it assembled so much mass so early. The presence of dark matter also plays a central role in its rule-breaking nature. Because dark matter forms the backbone of cluster structure, understanding its distribution is essential. In El Gordo, the dark matter map reveals two distinct peaks, consistent with two large clusters combining. The strength of the lensing indicates that both peaks were substantial. If dark matter behaved differently, or if it somehow interacted more strongly with gas or galaxies, the collision would look different. But the clear separation observed suggests that dark matter passed through with minimal resistance, helping reveal the underlying physics of these enormous structures. Studying clusters like this helps astronomers refine their understanding of cosmology. El Gordo challenges the predicted rate at which large structures form. If one cluster can grow so quickly, perhaps the models estimating how early matter clumps together need adjustments. This doesn't mean the models are wrong, but it means the assumptions might need further refinement. The discovery encourages researchers to re-examine how dense early regions of the universe may have been, and whether high-density pockets could have allowed for unusually rapid formation. Even without diving into equations or complex theoretical frameworks, what matters for understanding why El Gordo breaks rules is grasping the simple sequence of what should happen in a universe growing from initial irregularities. Structures start small, they combine slowly, they gain mass over billions of years. They don't jump to extreme sizes early in cosmic history, yet El Gordo did. This difference is what keeps astronomers returning to it again and again. Not because it contradicts our understanding, but because it pushes the boundaries of what's expected. It invites researchers to look deeper into cluster formation, matter distribution, and cosmic evolution. When astronomers look at El Gordo, one of the first things they notice is that the cluster doesn't show the smooth, balanced shape of a system that has quietly existed for billions of years. Instead, it carries the unmistakable signs of a cosmic event that unfolded over extraordinary distances and equally extraordinary spans of time. The clues are not dramatic in the way explosions or flares might be. They're far more subtle, woven into the motions of galaxies, the distribution of dark matter, and the structure of gas that still holds the heat of a vast, slow collision. Understanding that collision helps reveal why El Gordo became the massive cluster it is, and why its formation stands out as one of the more surprising events in the universe. The first thing to know is that collisions between galaxy clusters do not resemble anything like the collisions we experience in daily life. They are not fast, noisy, or sudden. There is no impact that happens in a single moment. Instead, a cluster collision spans hundreds of millions of years. It is a gradual overlapping of two enormous systems, each stretching across millions of light years. They move toward each other under the pull of gravity, and as they begin to merge, the galaxies inside them continue on their paths. Those galaxies are so widely spaced that they almost never collide directly. What truly interacts during a cluster collision is the hot gas between the galaxies and the underlying dark matter halos that shape the entire structure. In the case of El Gordo, the collision was more than just a gentle merging of two ordinary clusters. It was an unusually energetic encounter between two massive systems that had already accumulated significant mass. This alone makes the story stand out because for two very heavy clusters to collide so early in the universe, both progenitor clusters needed to grow rapidly on their own before ever encountering one another. Each one had a long history preceding the merger, built from smaller groups that combined to form the two main structures that eventually collided. The traces of the collision are not hidden. They appear in the temperature of the gas. They appear in the distribution of light. They appear in the movements of galaxies. And they appear in the lensing patterns created by dark matter. Taken together, these clues form a picture of a collision powerful enough to leave marks that remain visible even after more than 7 billion years. One of the clearest indicators is the heated gas. Gas in galaxy clusters normally reaches high temperatures, but when two clusters collide, the gas from both systems meets at tremendous speeds. Since galaxies pass through each other easily, the gas becomes the main participant in the collision. As it slams together, it compresses and heats dramatically. The heat from this interaction produces shock waves that spread through the cluster, raising the temperature of the gas far beyond what a relaxed, non-merging cluster would produce. In El Gordo, the gas temperature is unusually high for its era, and the patterns of heat distribution show irregular shapes, exactly what one would expect from two large systems merging. X-ray observations reveal this clearly. Instead of seeing a smooth halo of hot gas centered around a calm, gravitational middle, astronomers see turbulence. They see clumps of heated material, elongated regions where shock fronts have travelled, and asymmetries that indicate the collision did not happen head-on. These features tell researchers that the encounter between the two clusters was complex and energetic, with one cluster moving through the other in a way that left long-lasting imprints. Another important clue lies in the distribution of galaxies. In a settled cluster, galaxies typically orbit around a common centre, moving in patterns that reflect the cluster's overall gravitational field. But in a merging cluster, the galaxy movements can be chaotic. Their velocities can spread over a wide range, indicating that the gravitational field is not stable. In El Gordo, the velocities of galaxies show significant variation, suggesting that the cluster has not yet fully settled after the collision. These galaxies are still adjusting to their positions within the combined gravitational field. Galaxies serve as discrete markers of the larger structure. They don't feel the same resistance as gas during collision, so they carry memories of the paths they took before and during the encounter. By measuring their velocities and positions, astronomers can reconstruct how the two clusters approached each other and how their paths influenced the final structure. In El Gordo, the galaxy data points toward a collision where one cluster passed through the other at a high relative speed, leaving behind an asymmetric arrangement. The behaviour of dark matter offers another window into the collision. Dark matter forms the largest component of a cluster's mass, shaping the gravitational field that holds galaxies and gas together. But unlike gas, dark matter does not experience friction. It passes through a collision with little resistance. This means that when two clusters merge, their dark matter halos continue moving forward with fewer disturbances, while the hot gas slows down because of the collision. In El Gordo, the distribution of dark matter inferred from gravitational lensing maps shows two major peaks offset from the gas distribution. This separation is one of the most telling signs of a cluster collision. It indicates that the dark matter passed through the collision relatively unaltered, while the gas lagged behind and heated up. The fact that the dark matter peaks remain distinct also suggests that the merger is relatively recent in cosmic terms. Over time, the dark matter from merging clusters gradually combines, but the clear presence of two peaks shows that the process is still ongoing at the time we observe the light. This separation between gas and dark matter also provides valuable information about the physics of dark matter itself. If dark matter interacted more strongly with other matter, it would have slowed during the collision. But the clear separation seen in El Gordo supports the idea that dark matter has very weak interactions beyond gravity. This observation helps researchers refine their understanding of dark matter properties, making El Gordo not just an unusual cluster, but an important laboratory for studying the unseen components of the universe. The Sunyaev-Zeldovich effect provides yet another way to trace the collision. When electrons in the hot gas interact with photons from the cosmic microwave background, they shift the energy of those photons. The size of this shift depends on the temperature of the gas and the amount of gas present. In El Gordo, the effect is particularly strong, reflecting both the enormous quantity of hot gas and its high temperature. The strength of this signal shows how dramatic the collision must have been, because such intense heating requires energy on a scale that only cluster mergers can produce. All these indicators together build a detailed picture of the collision. The two clusters approached each other, drawn by their mutual gravitational attraction. As they got closer, their galaxies continued moving within their respective halos. When the clusters finally overlapped, their galaxies largely passed through without direct interaction. But the gas collided forcefully, creating shock fronts and heating to extreme temperatures. The dark matter halos followed their trajectories with minimal resistance. After the initial pass-through, the clusters continued moving, with the galaxies and dark matter stretching away from the heated gas. The result is a structure with clear separation between components, heated gas in elongated shapes, and galaxies with a broad velocity distribution. This snapshot of the collision gives astronomers insight into the larger scale structure of the universe at the time. The fact that such a collision occurred so early suggests that the region where the clusters formed was unusually rich in matter. For two massive clusters to exist close enough to merge, their birthplaces had to be dense. These dense regions are thought to form naturally from variations in the early universe, but the specific region that produced El Gordo appears to have produced structures more quickly than others. That density allowed both progenitor clusters to grow rapidly. Smaller groups of galaxies fed into them, merging and adding mass. Dark matter collected around them, creating deep gravitational wells. When the two large clusters finally encountered each other, the collision became one of the most energetic known in the universe, leaving behind the signals astronomers now study. There's also something important to note about the scale of this event. When discussing a cluster collision, the word collision might suggest something sudden or violent in the way that we think of impacts. But this event unfolded over extraordinary time spans. Even the moment when the clusters passed through each other would have lasted hundreds of millions of years from beginning to end. Every change occurred slowly enough that if you could have stood near the edge of the cluster for your entire lifetime, you wouldn't see galaxies crashing or gas violently shifting. Instead, you would see quiet movement, drifting shapes, and subtle shifts. The energy involved is enormous, but the pace at which it unfolds is slow, steady, and almost gentle when observed on human timescales. This slow pace is part of what makes the evidence so intriguing. These large-scale patterns last for billions of years. The shock fronts remain visible for long periods because the gas takes so long to cool. The dark matter halos continue moving in their post-collision paths, leaving their imprint on lensing maps. The galaxies take enormous amounts of time to adjust to their new gravitational environment, and because the collision occurred more than 7 billion years ago, everything we see is frozen in a moment that already passed long before Earth formed. Studying such a distant event gives astronomers the rare opportunity to examine how early cluster mergers shaped the universe's structure. Most merging clusters that are easily observed are much closer and reflect the mature universe. El Gordo, on the other hand, reflects a time when the universe was still evolving rapidly. This makes it a particularly valuable example, not only for understanding collisions but also for understanding how massive structures formed when the universe was still young. As we continue exploring this cluster, more aspects of the collision reveal themselves through different kinds of observations. The gravitational effects show how mass moved. The heat patterns show where energy was concentrated. The galaxy velocities show how the merger changed their motions. And the separation between gas and dark matter shows what happened at a fundamental physics level. Taken together, this collision becomes a story written across billions of light years, imprinted on the structure of the cluster itself. And because the universe sends us light from different eras, we're able to read that story long after the event took place. When people first hear that El Gordo earned its nickname because of its mass, the first thought is usually to imagine countless galaxies packed tightly together. And while that's true in a basic sense, the actual explanation reaches much deeper than the number of visible galaxies drifting inside it. Most of the weight in a galaxy cluster doesn't come from the galaxies you can see with an ordinary telescope. Instead, it comes from components that are either too faint, too diffuse, or too invisible to detect directly. El Gordo is a perfect example of this. Its visible galaxies are only the beginning of the story. What makes it one of the most massive clusters ever found is the combined influence of three main ingredients: hot gas, dark matter, and a huge amount of hidden mass that reveals itself only through gravity. Understanding these components is essential for appreciating why this cluster stands out so dramatically among the cosmic giants scattered throughout the universe. A good place to begin is with the hot gas that fills the space between the galaxies. This gas is often overlooked because it doesn't appear in images of galaxies taken in visible wavelengths, but it forms one of the largest contributors to a cluster's ordinary, or baryonic matter. The gas inside El Gordo is extremely hot, much hotter than anything on Earth outside of a laboratory setting. Temperatures reach tens of millions of degrees, and sometimes even higher in regions affected by the collision that shaped the cluster. Gas at those temperatures emits X-rays, and these X-ray emissions provide one of the main ways astronomers measure the amount of mass a cluster contains. In El Gordo, the X-ray signal is exceptionally strong. The gas not only fills vast regions of the cluster, but is heated to unusually high temperatures. These temperatures are linked to the depth of the cluster's gravitational well, because the hotter the gas, the more energy it carries, and that energy comes from the force of gravity compressing it. For gas to reach the temperatures observed in El Gordo, the cluster must have an enormous gravitational pull, far beyond the levels seen in typical clusters of the same age. That level of gravitational compression is possible only when the mass of the system is very high, so the hot gas itself, although just one component of the cluster, offers strong evidence that El Gordo is far heavier than the universe should easily produce at that early time. Another key contribution to its mass comes from the dark matter that threads through the cluster. Dark matter cannot be seen through direct observation, but its presence reveals itself through gravity. Most of the matter in a galaxy cluster is dark matter. Without it, the entire structure would fall apart, the galaxies inside El Gordo would drift away, the hot gas would escape, and the cluster would not hold together as a unified system. Dark matter forms the backbone of the cluster, shaping the gravitational landscape that affects everything else inside it. In El Gordo, the distribution of dark matter is not straightforward. Instead, dark matter appears in two main concentrations, reflecting the cluster's turbulent history as a merging system. These concentrations align closely with the predictions of how dark matter behaves during cluster collisions. Since dark matter does not interact strongly with gas or other forms of ordinary matter, it passes through the collision relatively smoothly. That means the dark matter peaks in the cluster represent the original cores of the two progenitor clusters that came together. Over time, those cores will gradually blend, but at the moment we observe El Gordo, they are still separate enough to be distinguished through lensing measurements. The fact that the dark matter peaks are so prominent and so massive further supports the conclusion that both of the original clusters were extremely heavy before they merged. This adds another layer of mass to the overall system, helping explain why El Gordo ranks among the most massive clusters known. One of the strongest lines of evidence for how much dark matter the cluster contains comes from gravitational lensing. When light from galaxies behind El Gordo travels toward Earth, the gravity of the cluster bends that light, distorting the shapes of the background galaxies. This bending effect allows astronomers to map the mass distribution throughout the cluster. In El Gordo, the lensing signals are unusually strong. Background galaxies show significant stretching and warping, some in subtle patterns and others in more dramatic arcs. These distortions trace out the gravitational influence of dark matter, revealing where its largest concentrations lie. The strength of these distortions indicates that El Gordo has an immense amount of mass that cannot be accounted for by the visible galaxies or even the hot gas. Only dark matter can explain the scale of the gravitational lensing. This invisible mass outweighs the visible mass by a wide margin, making it one of the biggest portions of the cluster's total content. Because dark matter represents most of the mass in clusters, the more dark matter a system contains, the deeper its gravitational well becomes. El Gordo's dark matter content is large enough to create a gravitational field, strong enough to heat gas to extraordinary temperatures, accelerate galaxies to high velocities, and bend light in ways that make the cluster easy to detect despite its vast distance from Earth. Beyond the hot gas and dark matter, there is also a third category to consider. This isn't a separate substance, but rather a combination of all the hidden mass that comes together to form the gravitational backbone of the cluster. In galaxy clusters, hidden mass includes faint galaxies, dim stars, unresolved gas structures, and the remnants of old emerging events. These components don't dominate in the way dark matter does, but they contribute enough to make a measurable difference in the total mass estimate of the cluster. In El Gordo, these hidden sources of mass are significant because the cluster contains many galaxies too faint to detect individually with earlier instruments. As astronomers use more sensitive equipment, they continue to uncover additional faint galaxies and intra-cluster light that help fill out the picture of how much matter truly exists inside the system. Intra-cluster light is the faint glow produced by stars that do not belong to any single galaxy. These stars drift freely through the cluster, often the result of previous interactions or collisions within the system. Over billions of years, galaxies pass through one another. Tidal forces strip stars away, and those stars become part of the diffuse light that floats between galaxies. This faint glow, while not a major contributor to the cluster's total mass, still adds an important piece to the overall picture. In El Gordo, intracluster light indicates that many interactions have occurred, suggesting a long history of smaller mergers before the massive collision that shaped the cluster we observe today. These interactions contributed to the early growth of the progenitor clusters, helping them accumulate the mass needed to produce a cluster as heavy as El Gordo. Even with all these components, the biggest contribution to the cluster's mass still comes from dark matter. Ordinary matter, hot gas, stars, galaxies, and intracluster light, represents only a small fraction of the total mass. The rest comes from dark matter, which dominates the gravitational pull and shapes the behaviour of everything inside the cluster. Despite being invisible, its influence appears in the motions of galaxies, the temperature of gas, and the structure of lensing patterns. In El Gordo, the dark matter content is so high that it alone would place the cluster among the most massive known. When combined with the baryonic matter, the total mass becomes extraordinary. Understanding why El Gordo contains so much mass requires a closer look at the early universe. At the time this cluster formed, the universe was denser than it is today. Matter had not yet spread out as much, and gravity had more influence over shorter distances. This allowed structures to grow faster than they would in later periods. But even with these conditions, forming a cluster as massive as El Gordo still seems unusually rapid. The merging of two large clusters provided a way to accelerate this growth. Those two clusters must have formed in a region rich in matter, perhaps at the intersection of multiple filaments in the cosmic web. Being located at such a junction would have given them access to more material, enabling them to grow quickly before merging. The collision amplified their combined mass, creating a system large enough to produce the powerful X-ray emissions, strong lensing signals, and high galaxy velocities that distinguish El Gordo from ordinary clusters. Although merging is a common process in cluster formation, the scale of the collision observed in El Gordo suggests that the early environment was unusually favourable for producing massive structures. This environment provided the raw materials, while the collision provided the mechanism for rapid assembly. It's also helpful to consider how gas behaves inside clusters like El Gordo. The hot gas makes up most of the ordinary matter in the cluster, and it carries important information about the gravitational forces shaping the system. Because the gas is so hot, it emits X-rays that can be measured across vast distances. These X-rays indicate not only how hot the gas is, but also how dense it is. Gas density helps astronomers estimate how much matter is present, because the hotter and denser the gas, the deeper the gravitational potential must be. In El Gordo, the gas density is particularly high in certain regions, suggesting strong compression during the merging event. Gas compression happens when two clusters collide, and the pressure increases dramatically as their gas halos push against one another. This pressure produces shock waves that travel through the cluster, heating the gas as they move. These shock waves can remain visible in X-ray data long after the initial impact has passed. In El Gordo, the shock signatures are still present, showing elongated patterns and uneven temperature distributions. This unevenness is a direct consequence of the merger, and it continues to shape the cluster's appearance. The distribution of gas reveals where the most intense interactions occurred, and how the two progenitor clusters passed through each other. Dark matter, unlike gas, does not produce light or heat. Its distribution must be measured indirectly through its gravitational effects. In a relaxed cluster, dark matter forms a smooth centralized halo. But in a merging cluster, the dark matter peaks remain associated with the original cores of the colliding clusters. In El Gordo, lensing observations show two such peaks, indicating that the cluster has not yet fully relaxed into a single smooth structure. This makes sense given the timing of the collision. The light we observe today describes the cluster as it existed more than 7 billion years ago, during a period shortly after the merger. The separation of peaks reflects that stage of evolution. Together, the gas, dark matter, and hidden baryonic mass form a complete picture of why El Gordo is so heavy. Each component contributes in different ways, but they all combine to create one of the universe's largest gravitationally bound systems. The balance between these components determines how the cluster behaves, how it evolves, and how it appears in different observational wavelengths. This unusual combination of mass components is what gave the cluster its name. Researchers studying it recognized that its mass was far beyond the norm, even for large clusters. The nickname El Gordo reflects this extreme nature, but the name also captures something about the surprise the cluster evoked when first discovered. It is not just heavy, it is extraordinarily heavy at a point in cosmic history when such mass should have been rare. When astronomers study a distant galaxy cluster like El Gordo, they're not looking at it as it exists today. They're seeing it as it was when the light began its journey across the universe, long before the Earth formed, long before the Sun ignited, and long before life appeared to observe anything at all. This idea can feel unusual at first because in everyday experience, we see things in the moment they're happening. A streetlight turning on, a bird flying past, a car passing through an intersection. Everything arrives in real time. But the universe doesn't deliver its distant stories on a real-time schedule. Light takes time to travel, even when it moves faster than anything else in existence. The farther away an object is, the older the information becomes by the time it reaches us. That delay becomes an essential part of understanding why El Gordo appears the way it does, and why its light tells us something important about the universe's early history. El Gordo sits at a distance of over 7 billion light-years from Earth. That means the light we observe today left the cluster more than 7 billion years ago. When that light began travelling toward us, the universe was much younger. It had only lived about half its current age. Galaxies were forming at different rates, stars were being born in greater abundance, and cosmic structures were still evolving rapidly. El Gordo was already massive during that time, which is part of why it intrigues astronomers so deeply. Its light comes from a moment when the universe should have been too young to host such an enormous structure. But the fact that we see it in that early state reveals something important about how the universe grows. One reason the cluster's ancient light tells such a compelling story is that looking across huge distances in space is also looking backward across time. Light doesn't arrive instantly. It has to cross immense distances. In the case of El Gordo, that journey took longer than human civilization has existed. It took longer than the age of the Earth itself. When we observe its faint glow through powerful telescopes, what we're truly seeing is a moment preserved from a different era. The cluster continues to exist today, and it has likely evolved significantly in the time since its light left, but that later version remains invisible to us. We can only observe the earlier stage because that is the only light that has reached our planet so far. This idea is central to astronomy. Telescopes are time machines in a very literal sense. They don't pull objects toward us. They simply receive light that has been travelling for millions or billions of years. Each photon carries a record of the universe's past. When those photons reach an instrument on Earth, or aboard a space telescope, they bring with them information about conditions that existed long before our species had language or tools, or even the ability to imagine what a galaxy cluster might be. In El Gordo's case, this ancient light is particularly valuable because it captures the cluster at a stage that challenges expectations. At 7 billion light-years away, the universe was still settling into patterns that define its large-scale structure. Small galaxies were merging into larger ones. Groups of galaxies were assembling into early clusters. But enormous clusters of galaxies, the kind that dominate the modern universe, were not supposed to be common at that time. They take billions upon billions of years to grow. Seeing a cluster as massive as El Gordo at such a young cosmic age is a reminder that the universe doesn't always follow the patterns we expect. The reason this matters so much is that light from different distances tells us how structures evolved over time. Close objects represent the universe as it exists today. Slightly farther ones show earlier stages. Extremely distant ones reveal moments from the universe's infancy. By comparing clusters at different distances, astronomers can trace the timeline of cosmic growth. Most clusters at El Gordo's distance fit comfortably into that timeline. They are large, but not enormous. They are developed, but not fully mature. El Gordo, however, appears far ahead of schedule. Another reason its ancient light stands out is that it reveals details about the collision that shaped the cluster. When two massive clusters collide, the effects last a long time, but they eventually settle. If we observed a merging cluster in the modern universe, we would see the later stages of that process. But El Gordo's distance means we're observing it when the collision was still fresh in cosmic terms. The shock waves had not yet dissipated. The hot gas was still strongly heated. The dark matter halos had not fully blended. That early observation gives astronomers valuable insight into how massive cluster mergers unfold. The light doesn't just show the collision, it also shows the galaxies inside the cluster at an earlier stage in their development. Some of those galaxies were still forming stars at a rapid pace, others were interacting with neighbours. The mix of galaxy types at that time reflects a younger, more dynamic universe. These galaxies are not the same ones we see in local clusters today. Over billions of years, they would have evolved, merged, and changed dramatically. But because the light left so long ago, we see them at the moment when they were still adjusting to the effects of the larger collision. Looking at El Gordo's ancient light also offers insight into the behaviour of dark matter. During a collision, dark matter halos pass through each other with little resistance. That behaviour leaves distinct signatures in lensing maps. These signatures look different in the early stages of a merger compared to the later stages. Because the light we observe left while the cluster was still in transition, it reveals details about dark matter that would be difficult to detect in older clusters. It shows the separation between dark matter peaks and the hot gas. It shows how the halos responded to the collision before they gradually blended. These details are crucial for understanding the fundamental properties of dark matter, which remains one of the universe's biggest mysteries. One subtle yet important detail about El Gordo's ancient light involves its redshift. As the universe expands, light stretches. That stretching shifts the light toward longer wavelengths, making distant objects appear redder than they originally were. The amount of this redshift indicates how far the light has travelled and how long it has been in motion. In El Gordo's case, the redshift is significant enough to place it firmly in the category of early massive clusters. This redshift measurement becomes a timestamp, letting astronomers determine the cluster's age at the moment the light left it. The expansion of the universe adds another layer of meaning to this. When the light we see today first left El Gordo, the cluster was much closer to our region of space than it is now. The universe has expanded significantly since then, so the distance the light travelled is not the same as the distance the cluster currently sits. In fact, the cluster has been moving away from us during the entire journey of its light. That movement adds complexity to the calculation, but it also helps reveal the universe's expansion rate at different points in time. Observing clusters like El Gordo helps refine measurements of this expansion, providing clues about how fast the universe grew and how dark energy influences that growth. Another interesting aspect of receiving ancient light is that different wavelengths carry different information. Visible light from the galaxies shows their shapes and brightness. X-ray light from the gas shows temperature and density. Microwave data from the Sunyaev-Zeldovich effect shows how the cluster alters the cosmic microwave background. Each type of light was emitted at the same moment, but arrives with different signatures because of how it travelled, and how the cluster interacts with those wavelengths. This variety gives astronomers a multi-layered view of the cluster. It allows them to reconstruct the conditions at the time the light began its journey. All these observations help build a picture of El Gordo as it existed in the early universe. But the cluster didn't freeze in that state once its light left. It continued evolving, it continued merging, it continued accumulating mass. The El Gordo that exists today is almost certainly different from the one we observe. It has had billions of years to grow and settle. The galaxies inside have aged. The gas has cooled in some regions and heated in others. The dark matter halos have blended more smoothly. But none of this is visible to us yet because the light reflecting those changes has not reached Earth. This delay creates an interesting paradox. The version of El Gordo we study may no longer exist in its observed form. The light is a preserved moment from a distant past. That preserved moment is incredibly useful scientifically, but it also means that we are always studying earlier stages of the universe, rather than its present state. Everything we observe outside the local cosmos is a memory carried by light. This idea becomes especially meaningful when thinking about the large-scale structure of the universe. When astronomers talk about the early universe, they're not referring to something theoretical or imagined. They're referring to real images and data. These images are not photographs of the past in the artistic sense. They are the actual photons that left distant clusters when the universe was much younger. Observing them is like reading pages of a cosmic history book, where each page comes from a different era and reveals different stages of growth. El Gordo's light comes from a particularly important page in that book. It represents a time when large-scale structures were forming rapidly. It shows a collision still unfolding. It shows galaxies not yet settled. It shows a universe filled with motion, heat, and change. And it shows a cluster that somehow grew faster than expected, defying the timeline used to explain most other massive structures. One reason astronomers value ancient light is that it provides a direct way to test theories about cosmic evolution. Computer simulations attempt to recreate how the universe formed, how dark matter clumped, how gas cooled, and how galaxies assembled. But those simulations need real data to confirm whether they match the universe we observe. Clusters like El Gordo offer that data. They allow researchers to compare predicted structures with actual ones. And when a cluster appears that doesn't fit the prediction, it signals that the model might need adjustment. El Gordo's presence at such an early time forces scientists to revisit assumptions about how quickly matter can gather. Another way that ancient light deepens our understanding comes from comparing El Gordo with other clusters at similar distances. Some clusters near its distance are massive, but not unusually so. Others are still forming. El Gordo sits at the extreme end of that distribution. It isn't alone in the early universe, but it belongs to a rare class of clusters that formed quickly. Studying these rare examples helps astronomers understand how the universe handles outliers. It also helps them recognize whether El Gordo's truly unusual or part of a broader population of fast-forming clusters that remain difficult to detect. The young universe had conditions that were different from what we see now. Matter was more densely packed. Gas was hotter. Galaxies were forming rapidly. Under those conditions, collisions were more likely. But even with those advantages, forming a cluster as massive as El Gordo required a perfect set of circumstances. The region of space it formed in likely had higher than average density. Those dense regions became the birthplaces of the first large clusters. But El Gordo's extreme size still suggests that it had access to an unusually large amount of material. Understanding why its light comes from such a young era involves more than just distance and time. It also involves the energy of the collision. When two massive clusters collide, the heat generated by the shock waves becomes locked into the gas. That heat takes billions of years to dissipate. So when the light we observe from El Gordo left the cluster, the heat of the collision was still fresh. That heat radiates in X-rays and influences the Sunyaev-Zeldovich effect. Because of that, the ancient light carries information about the collision in its earlier stages. This ancient light also offers insight into how galaxies respond to large-scale forces. Some galaxies inside the cluster appear distorted or stretched because of gravitational interactions. Others have unusual star formation patterns. These patterns wouldn't be visible in a cluster of the same mass in the modern universe, because the collision effects would have faded long ago. But El Gordo's distance freezes those effects in their early phase. Looking at such an early moment in cosmic history helps connect the dots between different stages of cluster evolution. It shows how smaller groups merge into larger structures. It shows how dark matter halos interact. It shows how gas heats and cools in response to collisions. Without these early snapshots, astronomers would have a gap in their knowledge, unable to see the formative years of the universe's largest systems. When astronomers first realized that El Gordo was something extraordinary, they faced an immediate challenge. How do you measure the mass of a structure so distant that its light began travelling toward Earth before our planet even existed? How do you weigh something made not only of stars and gas, but also of an invisible substance that doesn't emit or reflect any light at all? It sounds impossible at a glance, yet scientists have developed methods that allow them to measure objects across the universe with remarkable precision. They don't need to visit these places or send probes. They don't need to reach out and touch the cluster. Instead, they study the light, the heat, the motion, and the gravity. These tools become their instruments of measurement, turning faint signals into quantitative knowledge. A massive cluster like El Gordo cannot be measured with a single technique. One method might show the number of galaxies, another reveals the temperature of the gas, another traces the distribution of dark matter. Each approach adds a piece to the puzzle, and because different components respond in different ways to gravity, combining several techniques allows astronomers to build a complete picture, one that reveals not only the cluster's mass but also its structure and history. One of the first methods used to measure El Gordo involved counting galaxies. At first glance, this sounds simple, like tallying stars in the sky, but it requires careful work because many galaxies overlap in images and others are so faint that only deep exposures can reveal them. Astronomers look for clusters of galaxies that share similar redshifts, meaning the galaxies are all travelling away from us at similar speeds due to the expansion of the universe. When galaxies share a redshift, it indicates they're likely part of the same structure, rather than random alignments along the line of sight. In El Gordo's case, the concentration of galaxies at the same redshift was so strong that it immediately suggested a large cluster. This gave the first rough estimate of its mass, although galaxy counts alone can't provide a detailed measurement, because the galaxies themselves make up only a small fraction of the total mass. Still, the number and brightness of the galaxies offered a valuable starting point. It showed that the cluster was massive enough to gather a large community of galaxies into one region. Another tool scientists used was spectroscopy. By dispersing the light from individual galaxies, they can measure the precise redshift of each one. This reveals not only how far away the galaxies are, but also how fast they're moving relative to the cluster's centre. The spread in velocities, known as velocity dispersion, provides a measurement of how deep the gravitational well must be. If galaxies inside a cluster are moving very fast, then gravity must be strong enough to hold them in place. In El Gordo, the velocity dispersion was surprisingly large. Galaxies were moving at speeds that indicated powerful gravitational forces. That high speed showed that the cluster must be extremely massive. But galaxy speeds alone don't account for dark matter or gas. They simply provide a direct measurement of the gravitational potential. So the next step involves studying the hot gas inside the cluster. Gas in galaxy clusters is one of the main contributors to the observable mass. It fills the space between galaxies and reaches temperatures so high that it emits X-rays. Observing the X-ray emission allows astronomers to measure the gas temperature, density, and distribution. X-ray telescopes like those used to study El Gordo show that the hotter the gas, the stronger the gravity holding it in place. Heat is a response to gravitational compression. If gas is heated to tens of millions of degrees, then the cluster must have a deep gravitational well. In El Gordo, the gas temperatures were extraordinary. They weren't simply higher than average, they were among the highest measured in any cluster detected at that distance. That meant the gravitational pull was strong enough to compress the gas significantly, another sign of its massive size. The X-ray observations also revealed patterns of shock waves and irregular heat distributions, consistent with a collision. These patterns help astronomers understand how the cluster evolved, but they also influence mass calculations because irregularities in gas temperature can indicate the energy released by merging events. The more energetic the event, the more massive the progenitor clusters must have been. El Gordo's gas signatures showed that the collision was extremely energetic, meaning both colliding systems were already very large. That gave further confidence that the total mass of the system was enormous. Another method used to measure the cluster's mass came from the Sunyaev-Zeldovich effect. This phenomenon occurs when photons from the cosmic microwave background pass through the hot gas in a cluster. As they interact with electrons in the gas, they gain a slight amount of energy, shifting their frequency. This shift is extremely subtle, but sensitive instruments can detect it. The magnitude of the shift depends on the density and temperature of the gas. In El Gordo, the shift was significant, suggesting that the cluster had an exceptionally large amount of hot gas. Combined with X-ray measurements, this helped refine estimates of the cluster's mass, providing a cross-check to ensure that the measurements were consistent. Each of these methods gave part of the story, but to measure the full mass, including dark matter, scientists turned to one of the most powerful tools in astronomy, gravitational lensing. When light from distant galaxies travels past an extremely massive object like a galaxy cluster, gravity bends its path. This bending causes distortions in the appearance of those background galaxies. Some appear stretched, some appear curved, others become magnified. In rare cases, strong lensing can produce arcs or multiple images of the same galaxy. By mapping how the background galaxies deform, astronomers can reconstruct the mass distribution of the cluster responsible for the lensing. This method doesn't rely on any assumptions about the type of matter involved. It detects mass directly through its gravitational influence. In El Gordo, the lensing maps showed strong distortions across a wide region. The strength of these distortions indicated that the cluster contained an extraordinary amount of mass, far more than could be explained by visible galaxies or hot gas alone. These distortions highlighted the distribution of dark matter, showing two main concentrations that reflected the merging history of the cluster. The gravitational lensing method is particularly valuable because it offers a direct measure of total mass. It doesn't require interpreting temperature, gas density, or galaxy speeds. Instead, it uses the shape of space itself as a measuring tool. El Gordo's lensing signals were among the strongest for a cluster at its distance, supporting the conclusion that it ranked among the most massive clusters ever detected. What makes gravitational lensing so powerful is that it reveals where mass resides. In El Gordo, the lensing map showed that dark matter was clustered in regions that didn't always match the distribution of gas. This separation is typical in merging clusters and provided important insight into the collision that shaped the system. It also validated the earlier measurements from X-rays and the Sunyaev-Zeldovich effect, showing that all the observational methods were pointing in the same direction. Once each method provided its own estimate of the mass, astronomers combined them to refine the total. Using different tools is essential, because every method comes with its own uncertainties. Gas temperature can be influenced by shock waves. Galaxy velocities can be influenced by local gravitational effects. The Sunyaev-Zeldovich effect depends on gas properties that may vary across the cluster, and gravitational lensing can be sensitive to the alignment of background galaxies. But when all these methods converge, confidence grows. In El Gordo's case, each method indicated extremely high mass. The numbers matched closely enough to confirm that the cluster was truly enormous. This agreement among methods gave astronomers the certainty they needed to classify El Gordo not just as large, but as one of the most massive clusters known. Measuring something so distant also involves understanding how distance itself affects observations. Because the universe expands, objects at great distances appear dimmer and their light becomes stretched. This stretching, known as redshift, helps calibrate the distance to El Gordo. Once the distance is known, scientists can factor in how the universe evolved between the time the light left the cluster and the time it arrived at Earth. This context is crucial for interpreting the cluster's properties correctly. Another challenge in measuring its mass is accounting for projection effects. When observing a distant cluster, scientists see it in 2 dimensions, but the cluster exists in 3. Mass could be concentrated in regions that appear aligned along the line of sight. To overcome this, astronomers combine lensing maps with spectroscopic data, which reveals galaxy motions along the 3rd dimension. This combination helps separate overlapping structures from actual mass concentrations. El Gordo also requires careful handling of its merging nature. A merging cluster is not in equilibrium, meaning the gas is not distributed smoothly, and the galaxies are not orbiting in stable patterns. Mass estimates that assume equilibrium might lead to incorrect results. To avoid this, scientists rely more heavily on lensing, which does not depend on equilibrium. They also use simulations of merging clusters to compare observed patterns of gas and dark matter with those predicted by models. simulations play a major role in analysing El Gordo. Computer models can recreate merging events with different mass ratios, collision speeds, and angles. By comparing the simulated results to the observed structure, scientists can determine which scenarios match the cluster's actual appearance. These simulations help refine the mass estimates by revealing how merging affects measurements. They also help determine the likely collision velocity and the distribution of dark matter peaks. El Gordo's measurements also help test theories of cosmic structure formation. If a cluster this massive existed so early, scientists want to know how rare it should be. Simulations predict how many clusters of different masses should form at different points in time. El Gordo appears near the upper extreme of those predictions. It is not impossible according to current models, but it is highly unusual. Its mass, distance, and merging state combine to make it a rare object, one that offers valuable insight into the early universe. The different observational methods used to study El Gordo also help calibrate instruments and refine techniques. Clusters at different distances serve as benchmarks for different measurement types. Because El Gordo is so massive and so distant, it stretches the capabilities of these methods. It becomes a testing ground for how well instruments can detect faint signals, measure subtle distortions, and model complex structures. A particularly interesting aspect of measuring El Gordo is how the different components reveal themselves at different wavelengths. X-rays show the hot gas, optical light shows the galaxies, infrared observations reveal faint distant galaxies that optical telescopes might miss. Microwave observations detect the Sunyaev-Zeldovich effect, and radio observations can detect emissions from high-energy particles accelerated by the collision. These multi-wavelength datasets come together to build a detailed picture of the cluster. The process of combining all these measurements resembles assembling a mosaic. Each part of the electromagnetic spectrum adds another piece. Some pieces show structure, some show temperature, some show motion, some show gravity. The result is a detailed, consistent representation of the cluster's mass and shape. One reason scientists trust the measurements is that the different methods reinforce one another. If lensing alone suggested El Gordo was massive, there could be doubt. If gas temperature alone suggested great size, questions might remain. But every method points to the same conclusion. El Gordo is enormous, far more massive than clusters typically found at its distance. This convergence of evidence makes its measurement one of the most carefully supported mass estimates for any cluster in the early universe. Measuring something without touching it might seem counterintuitive in everyday life, but for astronomers, it is the standard approach. They use light as their tool, gravity as their indicator, and the behavior of matter as their guide. Through careful observation, cross-checking, and detailed analysis, they turn distant, ancient light into precise measurements of mass and structure. Astronomers have a way of finding beauty in the universe that doesn't depend on bright colours or dramatic explosions. Sometimes what captivates them most is the way gravity itself reshapes the path of light travelling across billions of years. This bending of light becomes a tool, a quiet and powerful one that allows scientists to see far beyond what telescopes alone could reveal. El Gordo, with its extraordinary mass, becomes one of these tools. It acts as a natural magnifying glass in space. Not because of any reflective surface or lens the way a human-made telescope has, but because gravity is strong enough to curve the fabric of space and redirect the light that passes near it. This effect turns El Gordo into a kind of gateway, letting astronomers observe galaxies even more distant than the cluster itself. Understanding how this happens begins with a simple idea. Light travels in straight lines, unless something bends those lines. In everyday life, this bending happens when light passes through glass or water. The change in medium alters the light's speed and direction, creating refraction. But in space, the bending works differently. There is nothing for the light to pass through. Instead, gravity stretches and curves space around massive objects. Light follows that curve as if it were the straightest path available. To the eye of an observer on Earth, this makes distant objects appear distorted or magnified because their light has been redirected along a different path. In the case of El Gordo, the cluster's mass is so large that it significantly bends the light coming from galaxies behind it. Those galaxies lie far beyond El Gordo, at distances even greater than 7 billion light-years. Their light travels toward Earth, but when it reaches the region near the cluster, the gravitational pull alters its direction. This bending creates a variety of visual effects. Some galaxies appear stretched into long, curved shapes. Others form arcs that wrap around the cluster's centre. In rare cases, multiple images of the same galaxy appear, each one created by a different path the light followed as it passed near the cluster. These distortions aren't just strange artifacts of cosmic coincidence, they are valuable scientific tools. When astronomers see how strongly light bends around a cluster, they can calculate how much mass the cluster must contain to produce that effect. The stronger the distortion, the heavier the cluster. This is one of the reasons El Gordo's mass became so clear. The distortions around it are substantial, pointing to enormous gravitational influence. Gravitational lensing comes in different strengths. There is weak lensing, where the distortions are subtle and require careful statistical analysis. And there is strong lensing, where the distortions are obvious even in a single image. El Gordo exhibits both. Weak lensing helps map the broader mass distribution, showing how dark matter spreads across the cluster. Strong lensing creates the dramatic arcs and stretched shapes that immediately reveal the cluster's power. The strong lensing effects in El Gordo are particularly useful because of how precise they are. When the light from a background galaxy is bent into an arc, the arc traces out where space has been curved. By measuring the arc's shape, astronomers can map the mass lying underneath. In El Gordo, these arcs occur in multiple regions. Each one corresponds to a different background galaxy, and each one gives a slightly different view of the cluster's gravitational field. When scientists combine these views, they produce detailed maps of the cluster's dark matter. These maps reveal something striking. Dark matter is not centered neatly in one spot. Instead, it forms two major concentrations, each corresponding to the core of one of the progenitor clusters that merge to form El Gordo. The strong lensing arcs cluster around these regions, tracing out the gravitational influence of the dark matter peaks. This provides evidence that the collision between the two clusters created a chaotic distribution, with the dark matter halos moving through each other and remaining separate for a long period. Weak lensing plays its own role in understanding the cluster. While strong lensing shows dramatic distortions near the cluster's centre, weak lensing reveals gentle stretches and shears far from the core. These patterns are much more subtle, almost impossible to detect by eye. But with careful statistical analysis, they show how mass spreads across a wide area. In El Gordo, weak lensing reveals a long elongated shape in the mass distribution, consistent with a high-speed collision that sent matter in extended directions. The combination of weak and strong lensing gives astronomers a complete picture. Strong lensing shows where the gravitational field is most intense. Weak lensing fills in the outer regions. Together, they create a detailed model of how mass is arranged inside the cluster. And because mass distribution is closely tied to how the cluster formed and evolved, lensing becomes one of the most powerful tools for understanding El Gordo's history. One of the most interesting aspects of gravitational lensing is how it makes the universe visible beyond the limits of telescopes. Light travelling from extremely distant galaxies is usually too faint to detect. But when it passes near a massive cluster, the bending of space magnifies the light. This magnification can brighten distant galaxies enough for telescopes to detect them. In some cases, galaxies more than twice as far away as El Gordo become visible, only because the cluster amplifies their light. This makes El Gordo not just an object of study, but also a tool for studying other objects. Astronomers use the cluster as a lens to observe galaxies that would otherwise remain invisible. These background galaxies come from eras even earlier than El Gordo. Their light began travelling toward us when the universe was much younger, possibly during the period when the first galaxies were forming. Without the magnifying effect of the cluster, this light would be too faint to detect. But thanks to gravitational lensing, these distant objects become accessible. This natural magnification has helped scientists learn more about the earliest phases of galaxy formation. By studying the lensed galaxies, they can analyse their structure, their star formation rates, and their evolution. This information fills in gaps about how galaxies develop over cosmic time. El Gordo becomes a gateway to that knowledge, not just because of its mass, but because of how it uses that mass to bend space. Another aspect of gravitational lensing that becomes important in clusters like El Gordo is time delay. When light from a distant galaxy takes multiple paths around a cluster, each path has a different length. That means the light arrives at slightly different times. For galaxies that vary in brightness, such as those experiencing supernovae or other events, these time delays can provide information about the geometry of the universe. Although El Gordo's lensing effects are mostly used for mapping its mass, time delay lensing remains a concept that helps refine measurements of cosmic expansion and dark energy. El Gordo's structure makes the lensing effect especially interesting. Because it is a merging cluster, the distribution of mass is not smooth. The two dark matter peaks create a lensing field with multiple strong regions. This produces arcs in several locations instead of one central region. Each lensing hotspot corresponds to a different mass concentration, allowing astronomers to study the collision in greater detail. The shapes of the arcs reveal that one part of the cluster is moving in a different direction from the other. This motion is another piece of evidence for the high-speed merger that shaped the cluster. The placement of the arcs even hints at the angle of the collision. If the two clusters collided head-on, the arcs might be more symmetric. But in El Gordo, the asymmetry suggests that the collision happened at an angle. One cluster passed slightly offset from the other, creating a more complex gravitational pattern. The light bending follows these patterns, offering subtle clues about the direction of motion and the energy of the event. The precision of lensing measurements allows astronomers to estimate the collision speed as well. In El Gordo, the merger appears to have been extremely fast, faster than many models predict for clusters in the early universe. This high speed adds another layer of intrigue because it implies that the region where the collision happened had a strong gravitational pull. The progenitor clusters must have been falling toward each other under the influence of a massive structure or a dense region of the cosmic web. All these insights come from the way El Gordo bends light. The bending becomes a form of measurement, a form of magnification, and a form of storytelling. It reveals the cluster's structure, its history, and its environment. And it does so without the cluster ever emitting its own visible signal about these aspects. The information comes from how it interacts with light, passing through its gravitational field. An interesting detail to consider is how this bending of light affects images taken by different telescopes. Space telescopes like Hubble produce some of the clearest images of lensing arcs. These images show the fine details of the distortions, which make it possible to model the mass distribution with high accuracy. Ground-based telescopes, equipped with adaptive optics, help contribute additional data, especially for weak lensing, where large-scale patterns are important. Multi-wavelength observations add another layer. Optical light shows the arcs directly. X-rays show where the hot gas lies, revealing how the gas behaves during the merger. Infrared light helps detect background galaxies that might be too faint in the optical range. Radio observations can show emissions from electrons accelerated by the collision. Each wavelength interacts with the gravitational lens differently, creating a more complete picture of the cluster and the galaxies behind it. The fact that El Gordo magnifies background galaxies also means that astronomers need to account for lensing when studying the cluster itself. The magnified galaxies can overlap with the cluster's galaxies in images, making it harder to separate them. Careful analysis is needed to distinguish which galaxies belong to the cluster and which belong to the background. This separation is crucial for building accurate models of the cluster's mass. The magnification also affects measurements of galaxy shapes. If a background galaxy is magnified, its apparent size becomes larger. This can cause confusion when estimating the properties of distant galaxies. But when astronomers account for lensing, they can reverse these distortions, retrieving the galaxy's true shape and brightness. This correction allows them to study galaxies that would otherwise be out of reach. As researchers continue to examine El Gordo, its gravitational lensing will remain one of its most valuable features. Not only does it reveal the cluster's mass, but it also helps uncover new details about galaxies that lie far beyond it. The cluster acts as a cosmic telescope, one that nature created through the fundamental laws of gravity. By using it, astronomers gain access to regions of space that would otherwise remain hidden. Because lensing depends on mass, clusters like El Gordo allow scientists to study the relationship between dark matter and the visible components. The fact that dark matter produces most of the lensing signal shows how dominant it is in the cluster. The visible galaxies and gas contribute only a small fraction. This helps refine theories about dark matter, especially regarding how it behaves during collisions. In El Gordo, the separation between gas and dark matter seen through lensing maps reinforces the idea that dark matter interacts very weakly with other forms of matter. The understanding gained from El Gordo's lensing effects also contributes to broader questions in cosmology. By studying how mass in clusters bends light, astronomers can refine estimates of cosmic expansion, dark energy, and the growth of structure over time. Clusters like El Gordo become important data points in these larger models. Their mass, distance, and lensing strength help build a more accurate picture of the universe's history. There are certain discoveries in astronomy that fit neatly into the existing framework of what scientists expect to find. A new galaxy somewhere in a quiet region of space might reflect the usual patterns of formation. A small cluster that grew over billions of years might fit the models comfortably. But every so often, something appears that pushes against those expectations. El Gordo is one of those rare cases. When researchers calculated its mass, distance, temperature, and merging history, they realized that this cluster raised questions that did not have easy answers. It wasn't simply large, it wasn't merely distant. It combined those properties in a way that placed it well outside the normal predictions for when clusters of its size should appear. To say that El Gordo shouldn't exist isn't a literal statement, but rather an acknowledgement that its existence became a challenge to the timing laid out by cosmological models. Understanding why this is the case means looking at how the universe forms structures over time. After the Big Bang, matter was distributed in a mostly uniform way, with only small fluctuations in density. These tiny variations provided the seeds for future galaxies and clusters. Regions with slightly higher density attracted more matter, growing slowly over cosmic time. Smaller structures formed first, larger ones formed later as the smaller ones merged. This sequence, known as hierarchical structure formation, is a central feature of cosmology. According to this framework, the most massive structures in the universe should appear relatively late, after billions of years of growth. El Gordo does not align with that timeline. The light we see from it comes from a time when the universe was only about half its current age, roughly 7 billion years ago. At that point, massive clusters were expected to exist, but not clusters of this scale. The amount of mass El Gordo had already gathered placed it among the largest clusters known today, even though it existed far earlier than most of those giants. This early appearance challenges the assumption that clusters need nearly the full age of the universe to reach such immense sizes. Astronomers began examining this discrepancy by looking at simulations of cosmic growth. These simulations use the known laws of physics, dark matter distribution, and cosmic expansion to predict how galaxies and clusters evolve. Under typical conditions, growing a cluster as massive as El Gordo by that early time would require a region of space with unusually high density. Such regions certainly exist in the universe, but they are rare. Even in those rare regions, forming two massive clusters and then merging them with the speed and energy required to match El Gordo's observed state becomes extremely unlikely. What makes the situation difficult is not just the amount of mass, but the timing of the merger. The collision that shaped El Gordo must have occurred shortly before the light we now observe left the cluster. That means the two progenitor clusters had to grow large independently, move toward each other at high speed, collide with enormous force, and still retain the clear separation between gas and dark matter seen in observations, all within a time window that seems narrower than expected. Each step adds another layer of improbability. Taken together, they create a scenario that leaves astronomers asking how such a massive and energetic event could have happened so early. Another reason El Gordo challenges expectations is the structure of its dark matter. Dark matter plays a major role in shaping clusters. Its gravitational pull gathers gas and galaxies, forming deep potential wells. In the early universe, dark matter had not yet had as much time to form large halos. Smaller halos existed, but the most massive ones typically form later as smaller ones merge. For El Gordo to have such large halos so early suggests that dark matter in that region collapsed into dense structures at an unusually fast rate. This type of rapid collapse is not impossible, but models predict that it should be rare. The cluster's gas temperature provides another clue about why its existence is surprising. Gas reaches higher temperatures in deeper gravitational wells. Because El Gordo's gas is extremely hot, this indicates that the gravitational pull must be extraordinarily strong. This in turn means the cluster's overall mass must have been very large even before the merger. Combined with the evidence that two already massive clusters collided, the system becomes even more unusual. Clusters with such high temperatures do exist in the modern universe, but they formed over much longer timescales. El Gordo reached similar conditions far sooner. One of the central puzzles comes from comparing El Gordo to predictions from the standard model of cosmology, known as LCDM. This model uses cold dark matter and dark energy as the foundation for explaining how structures grow and how the universe expands. LCDM is extremely successful in explaining a wide range of observations. It matches the cosmic microwave background. It matches the distribution of galaxies. It matches the growth of structure over time. But El Gordo sits near the extreme end of what LCDM allows. Some studies suggested that clusters like El Gordo might be so unlikely in standard cosmology that finding even one poses a challenge. That doesn't mean the model is wrong. It simply means that either the universe is more varied than simulations commonly assume, or that rare objects like El Gordo occur occasionally even if they fall on the far edge of probability. But to make that conclusion, astronomers need to understand what conditions in the early universe could have allowed such rapid cluster formation. One explanation is that El Gordo formed at the intersection of several cosmic filaments. These filaments make up the cosmic web, the large-scale structure of the universe. They act like highways for matter, directing gas, galaxies, and dark matter toward dense regions. If El Gordo's progenitor clusters formed at the convergence of multiple filaments, they would have had access to more material, allowing them to grow quickly. This type of environment could accelerate cluster formation, producing unusually large structures earlier than typical regions. Another possibility is that the merger between the progenitor clusters happened in a way that produced a particularly strong boost in mass concentration. A high-speed collision can compress gas, stir dark matter, and create shock waves that alter the cluster's structure. If the collision happened with the right angle, speed, and mass ratio, it could create conditions that amplify the cluster's mass signatures. This amplification would not change the total mass, but it could make the cluster appear more massive or more extreme than typical clusters of similar size. Even so, the underlying problem remains. Forming two massive clusters early enough to collide in such a dramatic event requires a region of the universe where matter density was much higher than average. Such regions do exist, but they are rare enough that researchers want to understand what might have made El Gordo's region particularly dense. Did small fluctuations in the cosmic microwave background create a region with more matter? Did dark matter behave differently in that region? Or did the region simply receive an unusually large amount of matter through the cosmic web? These questions don't have simple answers, but they push researchers to study clusters like El Gordo more closely. The cluster becomes a test case for understanding the limits of cosmic structure formation. If clusters like El Gordo are too rare to appear in standard cosmological models, then the models might need slight adjustments. The adjustments wouldn't be drastic, but they might involve refining assumptions about how matter flows through cosmic filaments, or how density fluctuations grew in the early universe. Another reason El Gordo challenges expectations is the speed of the collision that shaped it. Observations suggest that the progenitor clusters collided at very high velocity. High-speed collisions require strong gravitational influence. For two clusters to reach such speeds, they must have been falling toward each other from a significant distance under the pull of their combined mass and possibly the mass of surrounding structures. Producing such speeds in the early universe is difficult because there has not been enough time for gravity to accelerate objects over long distances. This adds another layer to the puzzle. Some researchers have suggested that El Gordo might not be unique. There could be other massive early clusters that remain undetected because they lie at distances that are harder to observe. If more clusters like El Gordo exist, then the universe may form large structures earlier than expected. But if El Gordo remains one of the few known examples, then it becomes a rare outlier, one that pushes the boundaries of what models allow. The uncertainty surrounding its rarity is part of what makes the cluster so valuable. It helps refine the way simulations handle dense regions. It helps test assumptions about dark matter. It helps improve predictions about how often massive clusters should appear in the early universe. And it helps guide future surveys that search for similar clusters at similar distances. The merging nature of El Gordo adds another challenge. Because the cluster is not in equilibrium, its mass estimates depend heavily on lensing. While lensing is a reliable method, merging systems complicate the interpretation because the mass is not evenly distributed. Still, the consistency among different measurement methods gives scientists confidence that the mass truly is as large as it appears. Even so, the merging state raises questions about how fast the cluster could have grown in the time available. There is also the matter of galaxy evolution. The galaxies inside El Gordo show signs of being active, with some still forming stars at high rates. The early universe was a time of rapid star formation, but when clusters become very large, the galaxies often shut down star formation sooner because gas becomes heated and stripped. The presence of active galaxies inside such a massive cluster suggests that the cluster was still in a transitional phase when the light we now see left it. This transitional state adds another layer to the question of timing. How did the cluster reach such mass, while still hosting galaxies that look more like those in younger, smaller clusters? The more astronomers study El Gordo, the more its details become part of the ongoing discussion about how the universe grew. It doesn't break the rules of cosmology, but it sits near the edges of what those rules allow. It encourages scientists to refine their understanding of early cluster formation and to explore whether similar objects might be waiting to be discovered. Most of the mass inside El Gordo isn't something you can see directly. It isn't in the stars or in the glowing gas, or in anything releasing light that a telescope can capture. Instead, the majority of the cluster's weight lies in something invisible, something that can pass straight through matter without slowing down, something that only reveals itself through gravity. This strange and hidden substance is dark matter, and although it makes up most of the universe's mass, it remains one of the least understood ingredients of the cosmos. Clusters like El Gordo offer one of the best environments for learning how dark matter behaves, not because the cluster is peaceful or settled, but because it endured a dramatic collision that pushed dark matter into conditions where its properties become easier to observe indirectly. Every cluster contains dark matter. Without it, galaxies wouldn't stay grouped. The hot gas inside clusters would drift away. The structure itself would fall apart. Dark matter's gravity forms a framework that all other matter clings to. But what makes El Gordo so useful is the fact that the cluster is not relaxed. It is not a calm, settled halo of dark matter surrounding a well-behaved distribution of gas and galaxies. Instead, the cluster is still in the aftermath of a powerful merger. Two clusters came together with enormous speed, passing through one another in a way that separated dark matter from the gas. That separation tells scientists something crucial about dark matter's personality, how it behaves when confronted with extreme conditions. The gas inside a cluster behaves predictably during a collision. Because gas particles interact, collide, and slow each other down, the hot gas between merging clusters will pile up, compress, and heat. This interaction creates shock waves and leaves behind noticeable trails. You can map where the gas slowed down and where it spread because gas responds to pressure and friction. But dark matter does not behave like gas. It passes through other matter as if nothing were there. It does not heat up. It does not collide in the same way. It does not clump together because of direct interactions. Instead, dark matter simply follows gravitational paths, continuing through a collision almost undisturbed. El Gordo demonstrates this clearly. Observations show that the dark matter peaks are offset from the gas peaks. In other words, the gas slowed down during the collision, but the dark matter kept going. This separation is not something you would see if dark matter interacted strongly with ordinary matter or even with itself. If dark matter were made of particles that collided with one another frequently, they would slow down as the gas did. They would form a different shape. But the distinct separation seen in El Gordo suggests that dark matter has extremely weak self-interactions. It behaves almost as if it can move through both gas and other dark matter without any noticeable resistance, responding only to gravity. This observation supports the prevailing view that dark matter is cold and collisionless, meaning its particles move slowly on cosmic scales and interact only through gravity. El Gordo becomes a test case for evaluating these qualities. Scientists compare the distribution of dark matter in the cluster to the distribution in simulations. These simulations model how dark matter would behave under various assumptions about its properties. When the observed pattern matches the predictions of a model with weakly interacting dark matter, it strengthens confidence in that model. The fact that dark matter did not lag behind in the collision also helps rule out certain alternative theories. Some theories suggest that what we call dark matter might instead be a sign of modified gravity. But in a modified gravity framework, the distribution of gravitational effects would not necessarily separate from the gas distribution. The separation seen in El Gordo indicates that the mass producing the gravitational lensing is not tied to the visible gas, but rather to an invisible substance behaving independently. This strengthens the argument that dark matter is a real physical substance, rather than a modification to gravitational laws. The lensing maps of El Gordo show two distinct regions where dark matter resides. These regions correspond to the cores of the original clusters before the merger. The gas clouds associated with each cluster slowed down during the collision and now lie between the dark matter peaks. This clear offset provides a rare opportunity to measure the degree to which dark matter interacts. The more separation there is between gas and dark matter, the weaker the interactions must be. In El Gordo, the separation is substantial. This suggests that the dark matter particles do not collide frequently. Instead, they pass right through the dense gas and through one another. This low level of self-interaction tells scientists that dark matter likely consists of particles that do not couple strongly with ordinary matter. That doesn't reveal what the particles are, but it constrains the range of possibilities. By studying systems like El Gordo, scientists can rule out certain classes of particles that interact too strongly or too weakly. They can refine models that explain how dark matter fits into the universe's structure. Another important clue about dark matter's behaviour comes from the shape of the lensing maps. El Gordo's dark matter distribution is elongated, consistent with a high-speed collision. If dark matter interacted strongly, the peaks would be more rounded, because self-interaction would smooth the distribution. Instead, the lensing maps show sharp, distinct peaks. This suggests that dark matter keeps its structure even after a major collision. The particles maintain their distribution, drifting through space according to gravitational pathways rather than through collisional dynamics. El Gordo also helps scientists explore how dark matter influences galaxy formation. The galaxies in the cluster are orbiting within the dark matter halos. Their motions trace the gravitational field. When researchers measure the velocities of these galaxies, they are indirectly measuring dark matter's influence. In El Gordo, the galaxies move at high speeds, indicating that the gravitational field is deep. This supports the idea that the dark matter halo is massive and concentrated. The combination of galaxy motions and lensing data gives a consistent picture of a large structured dark matter distribution. One interesting detail is how galaxies remain associated with the dark matter peaks even after the collision. Because galaxies, like dark matter, do not experience much friction, they also pass through collisions without slowing down. Gas, on the other hand, slows dramatically. This difference in behaviour explains why galaxies remain close to dark matter peaks, while the gas lags behind. This pattern reinforces the conclusion that dark matter behaves more like galaxies than like gas. Both move through space primarily under the influence of gravity. El Gordo's merging state helps scientists test whether dark matter has hidden interactions that only appear under extreme conditions. Some theories propose that dark matter particles might collide in ways that do not involve electromagnetic forces, but instead involve exotic interactions not found in ordinary matter. If such interactions existed, they might become noticeable in high-energy collisions between galaxy clusters. El Gordo, with its unusually high-speed merger, provides one of the best opportunities to look for these interactions. The clean separation between gas and dark matter suggests that such interactions, if they exist at all, must be extremely weak. Studying El Gordo also helps scientists understand the role of dark matter in shaping the cluster's evolution. Dark matter determines how the cluster assembled. It sets the gravitational potential. It dictates how gas is heated and where galaxies form. Without dark matter, the cluster would not have become as massive or as structured as it is. The amount of dark matter present also influences the cluster's future evolution, determining how quickly it will settle and how the gas will redistribute after the collision. Because dark matter is so dominant, its presence forms the underlying skeleton that every other component follows. Another aspect of dark matter's personality emerges from how the cluster's mass is concentrated. In El Gordo, the dark matter halos are dense, indicating that the matter in those regions collapsed early. Early collapse requires regions with higher than average density in the early universe. These dense regions draw in matter more quickly, forming dark matter halos that become the seeds of large clusters. The early formation of such halos is part of what allowed El Gordo to become so massive. This rapid collapse shows that dark matter behaved predictably, gathering according to gravity, but with more material available in that region than in typical areas. The size of the dark matter halo also affects how galaxies inside the cluster evolve. A deeper gravitational well means stronger tidal forces, more interactions, and more stripping of gas from galaxies. This can influence star formation rates, galaxy shapes, and the movement of galaxies through the cluster. In a young cluster like El Gordo, these processes are still ongoing. The dark matter halo has a direct effect on how the galaxies will evolve over billions of years. By studying how dark matter shaped El Gordo, scientists learn more about how dark matter shapes the universe. Every large structure in the cosmos formed because dark matter provided the gravitational framework. In some regions, more dark matter was present, leading to the formation of massive clusters like El Gordo. In other regions, less dark matter was available, resulting in smaller structures. This unevenness in dark matter distribution explains why the universe contains both giant clusters and vast empty voids. El Gordo's lensing effect provides another important insight. The strength of the lensing signal shows how concentrated the dark matter is in certain regions. The more concentrated the dark matter, the stronger the gravitational pull. The cluster's strong lensing arcs suggest that the dark matter peaks are dense and compact. This density tells scientists about how dark matter clumps together. If dark matter particles interacted strongly with each other, they might not form such sharp peaks. Instead, they would spread out more evenly. The presence of sharp peaks suggests that dark matter clumps efficiently under gravity alone, without needing additional forces to hold it together. Dark matter also influences the temperature of the gas, because the dark matter halo compresses the gas, heating it. The gas temperatures in El Gordo provide indirect clues about the mass and distribution of dark matter. The extremely high gas temperatures measured in the cluster reflect a deep gravitational well. That gravitational well is shaped by the dark matter halo. The gas does not heat to such high levels without a massive amount of dark matter present. The merging state of El Gordo also lets scientists examine whether dark matter interacts with gas at all. If dark matter particles collided with gas particles, you might expect the dark matter peaks to lag slightly, or to show signs of heating. But observations show no such lag and no heat signature from dark matter. This reinforces the idea that dark matter does not interact with gas in the usual sense. It moves through the collision as though the gas were not there. Another subtle clue about dark matter's behaviour comes from the shape of the dark matter halos after the collision. The halos maintain their general structure even after passing through each other. This suggests that dark matter halos are robust under extreme conditions. If dark matter halos were fragile or easily disrupted, the collision would have scattered the dark matter in irregular patterns, but the halos remain distinct, showing that dark matter maintains its distribution through gravitational forces. By examining the distribution of dark matter in El Gordo, scientists can test different particle physics models. Some models predict that dark matter particles have slight self-interactions. Others predict no interactions at all. El Gordo provides one of the clearest pieces of evidence for extremely weak self-interactions. The clean separation between dark matter and gas suggests that dark matter particles rarely collide with anything, even under extreme conditions. This cluster also helps refine the estimated mass of dark matter particles. The behaviour of dark matter during the collision helps scientists constrain how massive the particles could be. If dark matter particles were too light, they would behave differently. If they were too heavy, their distribution would also differ. By comparing observations with simulations, researchers narrow down the possible mass range. Clusters like El Gordo become a kind of natural laboratory for studying dark matter. They provide conditions impossible to recreate on Earth. In accelerators, scientists can test theories of particle physics, but they cannot simulate the gravitational environment of a cluster collision. Only the universe itself provides that environment. El Gordo becomes one of the few places where dark matter's behaviour reveals itself clearly. As researchers continue to study the cluster, its dark matter distribution will keep offering clues. More detailed lensing maps, deeper X-ray observations, and more precise measurements of galaxy velocities will provide additional information about how dark matter shapes the cluster. The more scientists learn from clusters like El Gordo, the better they can refine theories of cosmic structure. There's a question woven through almost every area of cosmology, one that seems simple at first but becomes increasingly complex the deeper scientists go. It asks how fast the universe grows, not how fast galaxies travel on their own, or how fast stars burn through their fuel, but how the expansion of the universe itself changes over time. It's a question that influences everything from the size of cosmic structures to the fate of the universe billions of years from now. When astronomers look at El Gordo, they see more than a massive cluster. They see a clue, a signal that helps test the rate at which cosmic structures form and how the expansion of space affects that growth. The cluster becomes a point of comparison, a benchmark that helps scientists understand how matter clumped together in the early universe and how different eras of cosmic history shape the pace of that gathering. The first thing to understand is that the universe's expansion isn't uniform across all of its history. Shortly after the Big Bang, the universe expanded extremely fast. Over time, gravity began slowing that expansion as matter attracted more matter. Galaxies started forming. Clusters began to take shape. But billions of years later, something unexpected happened. Instead of slowing down continuously, the expansion began to accelerate. This acceleration is attributed to what scientists call dark energy, a form of energy that permeates space and seems to push the universe apart more rapidly as time goes on. Because of this change, clusters form under different conditions at different times. In the early universe, expansion slowed enough for matter to clump together. In the modern universe, faster expansion makes it harder for new massive structures to form. Gordo sits at an interesting point in this timeline. The light we see from it comes from a period when the expansion was still slowing, before dark energy became dominant. At that stage of cosmic history, the universe was dense enough and gravity strong enough to allow clusters to grow effectively. But even in that environment, forming a cluster as massive as Gordo remains unusual. The fact that it reached such size so early gives astronomers a way to test how fast structure formation occurred in that era. Structure formation and cosmic expansion are deeply connected. When the universe expands more slowly, matter has more time to gather. When expansion accelerates, it becomes harder for gravity to bring matter together. Clusters form through the slow pull of gravity over billions of years. Their growth depends on how quickly matter can fall inward and how much matter is available in a region. That process becomes easier when the universe is younger and denser. But despite those advantages, the presence of a cluster as massive as Gordo suggests that certain regions of space gathered matter faster than expected. To understand why this matters, it helps to look at how scientists model the universe. They use equations that describe how matter behaves under gravity, how dark matter clumps, and how dark energy stretches space. These models predict how many galaxy clusters of different sizes should exist at different points in time. These predictions form a statistical framework. According to that framework, extremely massive clusters should be increasingly rare the farther back you look. They need time to grow, and the earlier universe provides less of that time. Gordo stands out because it sits at the tail end of this distribution. It's not just massive for its distance, it's massive even when compared to modern clusters. This makes it a useful test of how well the models match reality. If clusters this large are too rare in simulations, then the models might need adjustment. The adjustments might be small, but even slight changes can alter the predicted rate of cosmic expansion, the timing of structure formation, or the behavior of dark matter. When scientists analyze clusters like Gordo, they look at several factors tied to cosmic growth. One of these is the halo mass function, which predicts how many dark matter halos should exist at different sizes and different ages of the universe. Massive halos are less common than small ones, and extremely massive halos are the rarest of all. Gordo's halo appears near the extreme end of what the models allow for its age. This makes it a valuable data point for checking whether the predictions hold up. Another factor is the growth rate of structure. This rate describes how quickly matter collects into halos. If the growth rate is high, massive clusters form earlier. If the growth rate is low, they form later. By comparing Gordo to clusters at different distances, scientists can map out how the growth rate changed over time. This helps test theories about dark energy. Dark energy slows down structure formation by accelerating the expansion. If dark energy were stronger or weaker than expected, it would affect how early massive clusters can appear. Gordo's mass suggests that the growth rate in its region must have been high. That doesn't mean the universe as a whole grew faster, but it does mean the local environment where Gordo formed had conditions that encouraged rapid accumulation of matter. The cluster becomes a marker of how dense that region was and how much matter flowed into it over time. One important piece of this puzzle comes from the cosmic web, the large-scale structure of the universe. The cosmic web consists of filaments, voids, and nodes where matter gathers. Clusters form at the intersections of filaments where multiple streams of matter converge. If El Gordo formed at such an intersection, it would have had access to more material than typical regions. This extra material helps explain how the cluster grew so fast, but it also raises questions about how common such intersections are. If regions like this are rare, then clusters like El Gordo should also be rare. If clusters like El Gordo are too common, then the models need refinement. The collision that shaped El Gordo adds another layer to the question of cosmic growth. For two massive clusters to collide, both clusters must already exist. This means the early universe must have produced two large halos in close proximity. Such halos grow by drawing matter from their surroundings. If the environment around El Gordo contained a high density of matter, then the halos could grow quickly. But for them to collide, they must also begin moving toward each other under gravity. This requires the gravitational pull of their combined mass, as well as the influence of the surrounding cosmic web. The speed of the collision tells scientists something about how deeply the gravitational potential well was shaped by the dark matter in that region. The unusual speed of the collision in El Gordo suggests that the gravitational environment was strong. That strength could indicate a region where matter density was above average. A region like that would support faster growth of structures and influence surrounding matter in ways that aligned with the rapid formation of the cluster. Even so, clusters like El Gordo push the limits of what standard cosmological models predict. They lie near the boundary of what is expected for early structure formation. They are not impossible, but they are highly unusual. This makes them important objects for studying how the universe grew and for checking whether the growth matched theoretical predictions. One question astronomers ask when studying clusters like El Gordo is whether the expansion of the universe changed in ways the models didn't fully capture. Dark energy became dominant several billion years after the light we see from El Gordo was emitted. During the time El Gordo formed, gravity was still influencing the pace of structure formation more directly. If the expansion rate at that time was slightly different than current models predict, it could influence how clusters formed. El Gordo becomes a test case for examining that possibility. Another question involves the early behavior of dark matter. Dark matter clumps under gravity, forming halos that become the building blocks of galaxies and clusters. If dark matter behaved slightly differently in the early universe, those differences could influence how fast halos grew. Clusters like El Gordo help test whether dark matter acted consistently across cosmic history, or whether there were subtle differences in how it clumped. The cluster also ties into the question of how quickly galaxies formed. Galaxies inside clusters like El Gordo formed stars at different rates depending on the era and environment. In the early universe, star formation was more active. Examining the galaxies inside El Gordo helps scientists see whether the cluster environment suppressed star formation earlier than usual or allowed it to continue. These details help refine models of how galaxy evolution connects to cluster growth and cosmic expansion. Another important aspect is how El Gordo influences measurements of the expansion rate. The expansion rate can be measured in several ways, using supernovae, the cosmic microwave background, or baryon acoustic oscillations. Clusters add another method. Their distribution in space depends on the expansion history. If clusters like El Gordo are more common than expected, it could indicate that the expansion rate at earlier times differed slightly from predictions. If they are rare but still within expected ranges, then the models remain sound. El Gordo's mass, distance, and merging state provide a combination of factors that make it especially useful. The mass shows how much matter gathered. The distance shows when it gathered. The merging state shows how active the cluster was at that time. All three together help determine whether the universe grew structures at the expected pace. When scientists examine the cluster through gravitational lensing, they see a distribution of dark matter that matches the high-speed collision scenario. This suggests that the cluster formed rapidly, but in a way consistent with gravitational processes. The lensing maps help reveal how early halos reached maturity. The strong lensing arcs show how concentrated the mass became. These clues help refine estimates of when the cluster formed and how quickly matter gathered. The hot gas inside the cluster carries information about the depth of the gravitational well. Its temperature reflects how much matter pulled inward. These temperatures help determine whether the cluster had enough time to grow. In El Gordo, the gas temperatures are extremely high, suggesting rapid formation. The Sunyaev-Zeldovich effect provides another way to measure the cluster's properties related to expansion. Because the effect depends on gas density and temperature, it offers insight into how much mass the cluster contains and how that mass affected the cosmic microwave background. This information helps test the growth of structure at that point in cosmic history. One of the most valuable aspects of studying El Gordo is that it helps refine the relationship between cosmic expansion and matter distribution. By comparing El Gordo to other clusters at various distances, researchers create a timeline of cluster formation. If clusters appear earlier than expected, the timeline shifts. If they appear later, it shifts again. El Gordo sits at a point in this timeline where extremely massive clusters are supposed to be rare. Its presence helps determine whether this rarity matches predictions or whether the models need adjustment. Astronomers also examine how El Gordo fits into the broader statistical distribution of clusters. If the cluster is an outlier, it becomes a data point that helps define the extremes of what the universe can produce. By understanding these extremes, scientists can refine the probabilities that govern structure formation. These probabilities tie directly to the rate of cosmic expansion, because expansion influences how much matter clumps together over time. As cosmology advances, researchers continue expanding surveys to find more clusters like El Gordo. New instruments allow deeper observations and better measurements. If several clusters with similar mass and distance appear, this would influence how fast the universe is thought to grow. If El Gordo remains one of only a few, it becomes a rare but valuable object for testing theoretical limits. Thinking about El Gordo as it exists in the ancient light that reaches us is one thing. Thinking about what it has become in the billions of years since that light left is another. The cluster we observe is frozen in time, preserved in the moment when its light began crossing space. But the real cluster continued evolving long after that. It kept merging, cooling, heating, stretching, and reshaping itself. The galaxies inside moved through long orbits. The stars continued burning through their fuel. The gas inside the cluster shifted under the influence of gravity. None of those changes are visible to us yet, but they still happened. So understanding the future of El Gordo means imagining what happens to a massive cluster as it ages, how its gravity influences everything inside it, and how its structure alters as billions of years pass. A cluster as large as El Gordo grows by drawing more matter inward. That matter falls in along the cosmic filaments that connect clusters to the rest of the universe. Even after the dramatic collision that shaped El Gordo at the time we observe it, there would still have been a supply of gas, small galaxies, and dark matter streams feeding into it. Over time, these flows continue adding mass. Smaller groups fall in. Some of them get torn apart by tidal forces, others merge intact. The result is that the cluster grows steadily larger, and its gravitational potential becomes deeper. The two dark matter halos that were still distinct in the early collision would, over time, settle into a single combined halo. Settling happens slowly. The collision we see in progress would have continued for billions of years after the moment preserved in the light reaching Earth. The dark matter peaks would gradually approach one another. The gas, which was initially spread unevenly because of the collision, would have begun mixing and cooling in some regions. Cooling is important because hot gas emits X-rays, and those emissions represent energy loss. Over long periods, gas gradually loses energy and sinks toward the cluster's center. As it does, it becomes denser. The center of the cluster grows more massive and structured. This process, while slow, marks the transition from a disturbed cluster to a more relaxed one. Relaxation does not involve complete stillness. Even relaxed clusters remain dynamic environments. Galaxies orbit through them along long paths. Gas continues flowing. Dark matter continues shaping gravitational wells. But the chaotic patterns produced by the collision would eventually smooth out. Shock waves dissipate. Temperature variations stabilize, and the cluster becomes more symmetric. El Gordo, in its contemporary form, would look far calmer than the version we observed from billions of years ago. The stars inside the cluster add their own part to this long-term evolution. Most stars inside cluster galaxies behave the same way they would anywhere else. They burn through their fuel, they change colour slowly. Some evolve into red giants and then settle into white dwarfs. Others explode as supernovae. But the environment of a cluster affects these processes indirectly. Over very long timescales, the motion of galaxies within the cluster changes the conditions for star formation. As galaxies fall through the hot gas of the cluster, some of their gas is stripped away. This stripping process reduces the amount of material available for forming new stars. As a galaxy loses its gas, it transitions from a star-forming system to one where older stars dominate. In El Gordo, this transformation would have accelerated after the collision. When two clusters merge, the turbulence and compression in the gas can trigger bursts of star formation in some galaxies. But after that brief burst, the stripping processes increase. The hot gas in the cluster creates pressure that pushes against the cooler gas inside galaxies. The faster a galaxy moves through the cluster, the more gas it loses. Over billions of years, many galaxies inside El Gordo would have gradually transitioned into systems with little star formation, containing mostly older stars. This is typical of large clusters. They become environments where galaxies age faster than they would in isolation. Another effect of the cluster's mass is how it influences the motion of galaxies. As the dark matter halos settle, the gravitational pull becomes more centralized. Galaxies follow orbits that take them around the cluster's center, though these orbits can be elongated, chaotic, or influenced by interactions with other galaxies. Over long enough timescales, some galaxies spiral inward slightly, especially if they interact gravitationally with others. These interactions exchange energy and can alter the paths of different galaxies. But this process is extremely slow and happens over many billions of years. Eventually, some galaxies may merge with others. In the dense core, galaxies are more likely to collide. Collisions between galaxies do not look like collisions between solid objects. They pass through each other, stretching and distorting under gravity. Stars rarely collide directly, but the galaxy's gas clouds heat, compress, and trigger bursts of star formation during these events. After repeated interactions, the central region of the cluster may grow an enormous central galaxy, sometimes called a CD galaxy. Many mature clusters have such central giants. If El Gordo followed the same path, then over billions of years, its core would have grown a massive central galaxy formed from the merging of several smaller ones. The dark matter halo provides the gravitational structure for this evolution. As the halos merge and settle, the cluster's shape becomes smoother. The two peaks merge into a single peak. This new peak becomes the anchor point for the orbits of galaxies. Gas gradually cools toward the center, but cooling takes time because the gas is extremely hot. In very massive clusters, gas can remain hot for billions of years before cooling enough to form new stars at the center. This slow cooling process influences how the cluster evolves, keeping the core bright in X-rays even after the rest of the cluster has settled. As the universe continues expanding, the large-scale environment around El Gordo would change. At the distance we observe it, cosmic expansion was slower than it is today. After billions of years, dark energy became dominant, accelerating the expansion. This acceleration affects how clusters evolve. In the modern universe, clusters still grow, but their growth slows because expansion pulls matter away faster. As space expands more rapidly, it becomes harder for distant matter to fall into clusters. El Gordo, like all clusters, eventually becomes isolated. Matter that might have fallen into it earlier becomes too far away, expanding away faster than gravity can pull it back. This isolation leads to a future where clusters become more self-contained. They grow less from external sources and more through internal evolution. Galaxies inside the cluster merge with one another. Gas settles into the core. Dark matter maintains the structure, but new infalling material becomes rare. The cluster stabilizes into a long-term configuration, shaped more by the stars and galaxies inside it than by anything outside. Considering the stars within El Gordo over even longer spans of time brings another layer to its future. Stars age differently depending on their mass. Massive stars burn quickly, living short but bright lives. Smaller stars like red dwarfs burn slowly and can last far longer than the current age of the universe. In a cluster as large as El Gordo, the population of stars includes many red dwarfs that will continue shining for trillions of years. Over these enormous spans, the cluster becomes a collection of ancient stars, long after the bright blue stars have burned out and long after star formation in the galaxies has ended. Some stars eventually drift away from their host galaxies because of gravitational interactions. A galaxy passing close to another can lose stars to the cluster at large. These stars become part of the intracluster light. A faint glow spread through the cluster. Over time, this glow grows brighter as more stars become unbound. In far future versions of the cluster, this intracluster light becomes a more significant feature. It creates a halo of faint starlight that stretches through the space between galaxies. Gas within the cluster also follows a long-term path. Hot gas emits X-rays as it cools, but cooling takes enormous amounts of time. In the cluster's centre, some gas may cool enough to form new stars long after most galaxies have ceased forming them. But in many massive clusters, feedback from supermassive black holes prevents the gas from cooling too quickly. These black holes release energy that reheats the gas, preventing it from forming new stars. If El Gordo hosts a central black hole in its largest galaxy, that black hole would play a role in regulating the cluster's long-term star formation. Another consideration is how the cluster interacts with the cosmic microwave background. As long as the gas remains hot, it continues affecting the background light that passes through it. This effect persists even as the cluster ages. The long-term evolution of the gas keeps the Sunyaev-Zeldovich effect active, though weaker as the gas cools. Over extremely long time scales, the gas loses energy and eventually cools enough that the effect becomes minimal. If we imagine the cluster billions of years beyond the moment we observe it, we see a structure that has transitioned from chaos to stability. The shock waves from the collision have dissipated. The gas has settled into a smoother distribution. The dark matter halo has become centrally concentrated. The galaxies have aged, with most forming new stars only rarely. The entire cluster becomes a stable, massive system drifting through an expanding universe. On even longer timescales, the expansion of the universe becomes more significant. Dark energy's influence grows stronger, and distant galaxies recede beyond what clusters can gravitationally affect. El Gordo, like all clusters, becomes part of an isolated pocket of matter. It no longer draws material from outside. Its internal structure becomes the sole influence on its evolution. Over trillions of years, galaxies inside the cluster merge until only a few remain. The stars inside them continue aging. White dwarfs cool into black dwarfs. Neutron stars and black holes persist. The cluster becomes a quiet environment filled with the remnants of stars. This far future evolution may seem remote, but it reveals something important about clusters like El Gordo. They are not static objects. Even after their dramatic early mergers, they continue changing. The stars inside them follow predictable paths of stellar evolution. The gas cools gradually. The dark matter halo remains the dominant force shaping their structure, and the expansion of the universe influences how they gather or lose matter. While the version of El Gordo we observe is young and energetic, the real cluster today has grown older, quieter, and more settled. It likely contains a more centralized dark matter halo, a more stable gas distribution, and galaxies that have aged significantly. The environment inside the cluster has slowed star formation, and the stars themselves have continued their natural cycles. But the full story continues far beyond what we can see. There is a certain quiet that tends to settle over the mind when you step back from the details of a massive cluster like El Gordo and let the full scale of its story settle in. Not the kind of quiet that feels empty, but the kind that shows up when something large enough to reshape your sense of size sits in front of you, long enough that the usual reference points fall away. El Gordo offers that kind of quiet because everything about it stretches beyond the boundaries of what a person experiences in the day-to-day world. Its mass, its distance, its age, its collision history, its future, and the sheer amount of matter moving through it are so far outside ordinary human scales that trying to hold it all at once becomes less about memorizing facts and more about letting the idea of immensity rearrange the way the universe feels. The first shift usually comes with the realization that the light we see from El Gordo left it more than 7 billion years ago. This is a sentence that can be understood quickly, but it takes longer to feel the weight of what that means. The light left before the Earth had continents that resemble the ones we know. It left before plants existed on land. It left before the moon's orbit expanded to its present distance, and it travelled across a universe that expanded beneath it. When the photons reached Earth, they arrived in a world that didn't exist when they began. Every single moment in human history happened after the light began crossing space. Every language, every tool, every culture, every discovery, every question about existence appeared during that journey. It takes time to let that kind of distance settle into the mind, because the scale is so large that it isn't something you can compare to a familiar experience. There's no object you can hold, no walk you can take, no measurement you can visualize that equals the distance light traveled to bring you the image of El Gordo. So instead of trying to convert it into something familiar, the mind eventually adjusts by stepping away from comparing. The scale becomes something you accept rather than something you measure. And once that shift happens, the universe begins to feel different. It becomes less like a distant place, and more like an environment you're already inside, one where size isn't something you fully grasp, but something you simply acknowledge. The second shift often appears when thinking about how clusters like El Gordo form. They don't appear all at once. They grow slowly over billions of years. They pull in matter from regions so large that even the word region barely captures it. They accumulate galaxies. They drag in gas heated to millions of degrees. They gather dark matter halos that don't interact with anything except gravity. And they do it all under the steady influence of the laws that govern the universe. There's nothing dramatic or sudden in the early growth of clusters, but occasionally something does become dramatic, like the collision that shaped El Gordo. Even then, the drama stretches across millions of years, so slowly that if a person could watch it unfold in real time, it would look like a still frame. The collision between the two progenitor clusters didn't produce a moment of impact. It produced a long, steady passing through. The gas heated, the dark matter moved forward, the galaxies continued their long orbits. Nothing in the cluster experienced anything like sudden shock, in the way humans understand the word. Everything took place on a timeline that stretches so far beyond a lifetime that the pace becomes inseparable from stillness. Slow processes like that reveal something about the universe. They show that motion doesn't have to be fast to be powerful. They show that evolution doesn't need abruptness to be meaningful, and they show that change can happen in ways that exceed ordinary perception but still produce structures of extraordinary scale. Another shift comes from thinking about mass. El Gordo carries a mass that reaches into the quadrillions of solar masses. Saying that number aloud doesn't really convey what it means. A single solar mass can be difficult enough to comprehend. The Sun contains most of the mass in the solar system. It has enough gravity to hold planets in orbit for billions of years. Yet El Gordo contains the mass of millions of trillions of suns, and most of that mass is dark matter, something invisible, something you cannot touch or see, something that passes through matter without slowing. The idea that most of the mass in the universe is something you cannot observe directly is another one of those quiet realizations that shifts how you think about existence. It highlights how much of reality is hidden behind the limits of our senses. Even though dark matter is invisible, its influence is unmistakable. It shapes the galaxies inside El Gordo. It pulls gas into clusters. It creates deep gravitational wells that heat matter to extreme temperatures. It bends light passing near it. And it creates lensing arcs that show where its mass is concentrated. The existence of these arcs offers a reminder that the universe leaves clues everywhere, even when those clues come from distortions that you'd never see in everyday life. It's a kind of subtlety that reveals how quiet the universe can be, while still shaping everything on the larger scales. There's also something grounding in thinking about how stars inside the cluster live their lives. Most of the stars inside El Gordo will spend their entire existence inside galaxies that orbit the cluster's center. They will never leave. They will move along paths determined by gravity, shifting slightly as galaxies interact. Some will be stripped from their galaxies and drift freely through the intra-cluster space. Over time, many of the galaxies will stop forming new stars, not because the stars have burned out, but because the gas needed to make new stars was removed by the cluster's hot environment. When that happens, the galaxies transition into older, quieter systems filled with long-lived stars. On even longer scales, the stars inside those galaxies will age. The massive ones will explode. The smaller ones will continue burning slowly. White dwarfs will cool. Neutron stars will remain. Black holes will drift quietly. All of this will happen long after the snapshot we observe. El Gordo stars will continue their evolution far beyond the era when the Earth is habitable, far beyond the time when the Sun becomes a red giant, and far beyond the disappearance of the last traces of humanity. The cluster's timeline far exceeds anything that appears in the cosmic moment where humans exist. Considering that kind of longevity has a way of changing how a person thinks about their own place in the universe. Not in a way that diminishes human experience, but in a way that places it inside a larger context. The fact that people exist at all, on a small planet, orbiting an ordinary star, inside a galaxy that drifts along one of the filaments connected to much larger structures, becomes something that feels remarkable rather than insignificant. The universe is not diminished by human presence, and humanity is not diminished by the universe's size. Both exist together, one unfolding within the other, following different timescales but sharing the same space. Another reflection arises from thinking about how the universe changes with time. When the light we see from El Gordo was released, the universe was in a different stage of expansion. Matter was more densely packed. Star formation was higher. Collisions between galaxies were more frequent. Clusters grew more quickly. The cosmos has shifted dramatically since then. It has expanded, cooled, and become dominated by dark energy. The structures that form now are shaped under different conditions than they were when El Gordo was in its early stages. This difference in conditions reveals how the universe is not static but evolving. It reminds anyone thinking about it that nothing in the cosmos stays fixed forever, not even the laws that govern how structures form. The laws stay the same, but the environment changes. Spending time with thoughts like this creates a sense of perspective that doesn't depend on grand statements or dramatic realizations. It grows gradually, in the same way clusters grow. A person begins with simple curiosity. That curiosity becomes interest. That interest becomes reflection. And that reflection turns into a broader sense of place. Not place in the sense of a specific location, but place in the sense of being part of something much larger. The universe becomes less of a distant abstraction and more of a familiar environment. even if its scale remains beyond anything the senses can truly grasp. El Gordo adds another layer to that reflection, because it represents one of the largest gravitationally bound structures known. It's a reminder that the universe produces scale in both directions. At one end, there are subatomic particles. At the other, there are clusters larger than entire superclusters of galaxies, and between those extremes lies everything from stars to planets to the space that people inhabit. Knowing that something as massive as El Gordo exists doesn't mean that everyday life becomes smaller. It simply means that the universe holds more variety than any one perspective can contain. Human experience fits into the universe not because of its size, but because of its ability to experience and reflect. There's a kind of comfort that comes with realizing that the universe contains structures that will continue evolving long after anything on Earth changes. These clusters will drift, merge, and age quietly, following trajectories set by gravity and shaped by the gradual cooling of the cosmos. Their stories extend far into the future, but even though their timescales exceed human timescales by unimaginable margins, the light they release becomes part of the human story because it reaches Earth and gives people the ability to understand their surroundings. If someone looks at an image of El Gordo, they might see arcs, galaxies, and glowing gas. But behind that image is a story stretching across billions of years. Behind that story is the physics that shaped it. And behind that physics is the quiet, consistent framework that keeps the universe operating. Knowing that such things exist can produce a feeling of steady calm, not because the universe is gentle, but because it is consistent. It's also worth remembering that the universe does not require understanding in order to function. Clusters form whether anyone observes them or not. Galaxies orbit whether anyone studies them or not. Stars burn with or without witnesses. But the fact that people can observe these things and make sense of them adds a layer of meaning. Human awareness becomes part of the universe simply by paying attention. That awareness does not change the universe, but it changes the experience of living inside it. Thinking about El Gordo in these terms turns the cluster into something more than an object of scientific interest. It becomes a point of connection, a way of seeing how the universe builds structures across unimaginable scales and how light carries those structures across unimaginable distances. It becomes a reminder that even though the universe is vast, people can still learn from it, reflect on it, and feel connected to it. As thoughts settle around these ideas, the sense of immensity becomes less overwhelming and more grounding. The size of El Gordo doesn't need to be understood all at once. It doesn't need to be measured in a way that feels personal. It can simply exist as part of the universe, the same universe that produces stars, planets, organisms, and people capable of asking questions about their place in it.